Before the first star burned, before the first atom assembled, before light knew itself as light, there was something else. Or perhaps there was nothing at all. This is the question that has haunted humanity since we first turned our gaze upward and wondered not just what fills the heavens, but what filled them first. What created the very first particle? It sounds like a simple question, the kind a child might ask on a quiet evening. But it is not simple. It is the loneliest question in all of existence, because every answer we have ever constructed, every theory we have ever proposed, every equation we have ever written, eventually collapses into this single, impossible moment. And in that collapse, we find ourselves standing at the edge of a darkness so profound that even the concept of darkness itself seems inadequate to describe it. We have always been obsessed with beginnings. The ancient Greeks imagined atoms falling through an infinite void, colliding by chance to form worlds. The Vedic sages of India spoke of cosmic cycles, universes born and destroyed in the breath of gods, each cycle lasting billions upon billions of years before dissolving back into formless potential. Medieval scholars debated whether time itself had a beginning or whether it stretched backward forever, an infinite regress that made their minds ache. And when the quantum theorists of the 20th century began to peer into the architecture of matter, they discovered something even stranger, that the universe might not need a creator at all. It might simply be a mathematical accident, a fluctuation in a field of probability, a glitch in the equations of reality itself. Yet none of these explanations, no matter how elegant or revolutionary, can escape the central problem. They all require something to already exist. A void to contain the atoms, a field to fluctuate, a probability to express itself. Even nothing, it seems, must first be something. This is the emotional paradox that sits at the heart of cosmology. To ask what created the first particle is to ask what existed when existence itself did not yet exist. It is to demand an answer from a time when time had no meaning, from a place where space had not yet unfurled. We are asking for a cause in a realm where causation itself may be an illusion, a byproduct of the universe we inhabit rather than a fundamental feature of reality. And yet we cannot stop asking. Because if we cannot understand the first moment, then everything that follows, every star, every galaxy, every thought in every mind, is built on a foundation we do not comprehend. We are living inside a mystery, and the mystery is not decorative. It is structural. It is load-bearing. Here a deeper question emerges, one that philosophers have circled for millennia without ever quite touching. What does it mean for something to come from nothing? Our intuition rebels against the idea. We live in a world where effects follow causes, where objects persist through time, where the present is always built from the scaffolding of the past. A tree comes from a seed. A river comes from rain. A thought comes from neurons firing in precise patterns. But trace any chain of causation backward far enough, and you arrive at a place where the chain itself must begin. And what stands before that first link? What creates the creator? The ancient Greeks had a word for this, the unmoved mover, the first cause that requires no cause of its own. But naming the problem is not the same as solving it. It is simply giving a shape to the void. Some have argued that the question itself is malformed, that asking what came before the first particle is like asking what lies north of the North Pole. It is a grammatical construction that feels meaningful but dissolves under scrutiny. Perhaps time is not a river flowing backward forever, but a closed loop, or a surface with no edge, or a dimension that emerges from something deeper. Perhaps the word before is an illusion, a cognitive artifact of minds that evolved to navigate a universe already in motion. But even if we accept this, Even if we agree that time itself has no absolute beginning, we are still left with the question of why anything exists at all. Why is there something rather than nothing? And why is that something structured in such a way that it can ask this question of itself? The terror of absolute nothing is difficult to hold in the mind for long. We think we understand what nothing means: an empty room, a silent night, the absence of sound or light or motion. But these are all something. A room still contains space. A night still contains time. True nothingness is not an empty container. It is the absence of the container itself. No space to be empty. No time in which to be silent. No laws of physics. No mathematical structures. No potential for anything to ever happen. It is a concept so alien to our experience that we can barely think it without immediately filling it with something. A void, a darkness, a waiting. But nothingness does not wait. It does not endure. It simply is not. And yet here we are, undeniably existing, in a universe filled with particles and forces and patterns. Somehow, existence clawed its way out of non-existence. Or perhaps it never had to, because non-existence was never truly possible. This is where the story bends in a direction that feels almost mystical, though it is grounded entirely in the mathematics of quantum mechanics. In the 20th century, physicists discovered that the vacuum, what we casually think of as empty space, is not empty at all. It seethes with activity, with particles flickering into existence and vanishing again in timescales so brief they seem to mock the very idea of being. These are called virtual particles, and they are not metaphors. They are real enough to produce measurable effects, to alter the behavior of atoms, to contribute to the structure of reality. The vacuum, it turns out, is a kind of restless potential, a field of possibility that never quite settles into stillness. And this raises a profound question. What if the first particle was not a thing that appeared in empty space, but a disturbance in this field of potential itself? What if the universe did not begin with matter, but with a transition, a shift from one state to another, a ripple that propagated outward and never stopped? But there is a deeper problem, one that gnaws at the edges of every theory. If the vacuum can produce particles spontaneously, what produced the vacuum? If the universe began as a quantum fluctuation, what set up the quantum field in which that fluctuation could occur? We have not escaped the infinite regress. We have only pushed it back one step. Perhaps the answer lies in the nature of mathematics itself. Some physicists have speculated that mathematical structures do not need to be instantiated by anything. They simply exist as abstract patterns, and our universe is one such pattern that happens to be self-aware. But this is not an explanation. It is a relabeling of the mystery. We are saying that the universe exists because certain equations are true, without addressing why those equations should have any connection to reality, or what it even means for an equation to be true in the absence of a universe to validate it. Others have proposed that the universe is eternal, that it has always existed in some form, cycling through phases of expansion and contraction, birth and death, and rebirth. This solves the problem of the first particle by denying that there ever was a first particle. But it does not solve the problem of existence itself. An eternal universe still requires an explanation for why it exists rather than not existing. And if the universe has been cycling forever, why is this cycle meaningful rather than arbitrary? What sustains it? What prevents it from collapsing into true nothingness? The ancient Vedic sages understood this paradox. They spoke of Brahman, the eternal reality that underlies all change, the ground of being that is never created and never destroyed. But this is not science. It is philosophy dressed in the language of myth. And yet it may be pointing towards something real, something our current theories have not yet learned to articulate. There is another possibility, one that sounds almost like science fiction but emerges naturally from the equations of quantum mechanics. What if the first particle was not the beginning of time, but the beginning of this timeline? What if the universe is constantly branching, splitting into parallel versions of itself with every quantum event, and the first particle we ask about is simply the first one in our branch of the cosmic tree? In this view, there is no single moment of creation, no absolute beginning. There is only an infinite web of possibilities, with our universe being one thread in a tapestry too vast to comprehend. But even this does not escape the original question. It only multiplies it. If there are infinite universes, each with its own first particle, what created the multiverse itself? What set the branching in motion? We are back where we started, staring into the abyss of origins. Yet the truth may be stranger than any of these options. Some theorists have begun to suggest that the question of the first particle is unanswerable not because we lack information, but because the question assumes a framework, time, causation, discrete objects, that did not exist in the earliest moments. Imagine trying to ask what color the universe was before light existed. The question is not merely difficult. It is incoherent. Color requires light, and light requires a universe in which electromagnetic waves can propagate. Before that, the concept of color has no meaning. In the same way, asking what created the first particle may require concepts of cause and effect that only make sense after particles already exist. We are trying to use the logic of the interior to understand the exterior, the rules of the game to explain why there is a game at all. And perhaps that is simply impossible. This is the awe and the dread that sits at the heart of cosmology. We are creatures who evolved to understand cause and effect, pattern and repetition, objects moving through space. But the origin of the universe may lie beyond these categories entirely. It may be that the first particle was not a thing that appeared, but a transition that rewrote the rules of reality from the inside out. Not a creation event, but a phase shift, a moment when the raw potential of existence crystallized into something we can recognize as matter and energy in time. And if that is true, then the first particle was not the beginning of the universe. It was the beginning of the kind of universe we can inhabit and understand. Before that, there may have been other kinds of existence entirely. Forms of being so alien to our experience that we have no language to describe them, no mathematics to model them, no instruments to detect them. And this is where the story must begin. Not with an answer, but with an acknowledgement. The first particle is a mystery that may never be solved, not because we lack the tools or the intelligence, but because the question itself may be reaching beyond the limits of what questions can do. We are asking existence to explain itself, and existence does not owe us an explanation. It simply is. And yet we cannot stop asking, because to ask is part of what it means to be human, to be conscious, to be a fragment of the universe that has somehow learned to look back at itself and wonder. The first particle may forever remain beyond our grasp, a singularity not just in space and time, but in understanding itself, but in reaching toward it, in constructing theories and discarding them, in building telescopes and particle accelerators and equations that fill blackboards. We are doing something profound. We are participating in the universe's attempt to know itself, and perhaps that is answer enough. There is a place between the stars where human intuition goes to die. It is called the vacuum, and we have been wrong about it for most of history. We imagined it as a kind of absolute absence, a stage emptied of all actors, a canvas wiped clean. The Greeks called it the void and feared it. Medieval philosophers argued over whether it could even exist, whether God would permit such a thing as true emptiness within his creation. And when the scientific revolution arrived, the vacuum became a laboratory concept, a condition we could approximate by pumping air from a chamber and watching what remained. But we were always looking at it wrong. We were treating it like a container, like a room that could be emptied. What we did not understand, what we could not have understood until the mathematics of the 20th century forced us to see it, is that the vacuum is not empty at all. It is the most active, the most restless, the most generative fabric in all of existence. It is a silent storm, and we are living inside it. This revelation came from quantum field theory, one of the strangest and most successful frameworks in the history of physics. The theory tells us that what we call empty space is actually filled with fields, invisible, intangible structures that permeate every point in the universe. There is a field for electrons, a field for photons, a field for every type of particle that exists. And these fields are never still. Even when no particles are present, the fields themselves are vibrating, oscillating, humming with an energy that never quite settles to zero. This is not a metaphor. It is a mathematical necessity, a consequence of Heisenberg's uncertainty principle, which states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. But the principle goes deeper than that. It tells us that even the vacuum itself cannot be perfectly defined. It cannot have zero energy and zero fluctuation at the same time. And so it vibrates. It churns. It seethes with possibility. What this means is almost too strange to accept. At every point in space, at every moment in time, particles are flickering into existence and vanishing again. Electrons and positrons, quarks and antiquarks, photons and gravitons, they emerge from the vacuum in pairs, exist for a fraction of a second so brief it defies human comprehension, and then annihilate each other, returning the borrowed energy to the field from which they came. These are called virtual particles, though the name is misleading. They are not illusions. They are not theoretical constructs. They produce real, measurable effects. They alter the energy levels of atoms. They contribute to the way light bends around massive objects. They are detected in laboratories around the world, every day, in experiments so precise that they can measure forces smaller than the weight of a single bacterium. The vacuum is not a passive backdrop. It is an active participant in the structure of reality itself. But there is a deeper problem lurking here, one that cosmologists have struggled with for decades. If the vacuum is constantly producing particles, why doesn't the universe fill up with them? Why isn't space an impenetrable foam of matter and antimatter, colliding and annihilating in an endless cascade? The answer lies in the brevity of their existence. Virtual particles live on borrowed time, and the debt must be repaid almost instantly. The more massive the particle, the shorter it can exist before the universe demands its energy back. A photon, which has no mass, can travel indefinitely. But an electron-positron pair can only exist for about 10 to 21 seconds before they must meet and destroy each other. This is the bargain the vacuum makes with reality. It can create something from nothing, but only for a moment. Only for the blink of an eye. And yet this is enough. Because in those moments, in those infinitesimal flickers of existence, the vacuum is shaping the universe. It is contributing to the forces that hold atoms together. It is influencing the way particles interact. It is, in a very real sense, the hidden scaffolding of everything we see. And this raises a question that cuts to the heart of cosmology. What if the first particle was not an exception to the rules, but an expression of them? What if the universe did not begin with some external creator reaching into nothingness and pulling out matter, but with the vacuum doing what it has always done, spontaneously generating particles from its own internal energy? In this view, the Big Bang was not a violation of the natural order. It was the natural order expressing itself at its most extreme. Imagine the vacuum not as a stable, eternal background, but as something capable of changing states, like water freezing into ice or boiling into steam. Perhaps in the earliest moments, the vacuum was in a different configuration, a higher energy state, inherently unstable. And perhaps it underwent a phase transition, a sudden shift that released enormous amounts of energy, energy that crystallized into the first particles, the first atoms, the first structures of matter and light. The universe, in this picture, is not a creation. It is a transformation, a ripple that never stopped spreading. Yet the truth may be stranger than even this. Some physicists have proposed that the vacuum itself has mass, that empty space weighs something, and that this weight is responsible for the accelerating expansion of the universe. They call it dark energy, though the name tells us almost nothing about what it actually is. What we know is that the vacuum seems to push outward, to drive galaxies apart, to stretch the fabric of space-time in ways that should not be possible if space were truly empty. And this suggests something profound, that the vacuum is not just a stage on which reality unfolds, but an actor in the play itself. It has properties. It has energy. It can change. And if it can change, then it can have a history. Which means that the vacuum we observe today may not be the same as the vacuum that existed in the earliest moments of the universe. Perhaps the first particle did not emerge from nothing. Perhaps it emerged from a different kind of something, a pre-vacuum, a proto-reality, a state of existence so unlike our own that we have no language to describe it. This is where modern quantum cosmology begins to echo ancient creation myths in ways that are both eerie and illuminating. The Vedic texts speak of the universe emerging from Akasha, a primordial ether that is neither matter nor energy, but the potential for both. The Chinese Tao Te Ching describes the Tao as the source of all things, something that exists before existence, a void that is somehow full. And the Kabbalistic tradition speaks of Tzimtzum, the contraction of infinite light to create space for the finite world. These are not scientific theories, but they are pointing toward the same intuition that quantum field theory has formalized, that nothingness is not the absence of everything, but the presence of something so fundamental, so pervasive, that we mistake it for emptiness. The ancients understood, in their own way, that the void is not a void at all. It is the womb of reality. But here a question emerges, one that feels almost cruel in its simplicity. If the vacuum is always producing particles, why don't we see them everywhere? Why isn't the world filled with spontaneous eruptions of matter, flashing into existence and vanishing again? The answer lies in the nature of energy and time. Virtual particles exist in a kind of quantum limbo, borrowing energy from the vacuum for such a short duration that they never quite become real in the way we understand realness. They are ghosts, traces, possibilities that flicker at the edge of existence without ever fully crossing over. But, and this is the astonishing part, under the right conditions, they can become real. If you place two metal plates very close together in a vacuum, something strange happens. The space between the plates restricts the types of virtual particles that can appear there, while the space outside the plates has no such restriction. This creates a pressure difference, and the plates are pushed together by the vacuum itself. This is called the Casimir effect, and it is direct, measurable proof that the vacuum has structure, that it can exert force, that it is not nothing. And this is where the story bends towards something even more unsettling. If virtual particles can become real under certain conditions, what conditions existed at the very beginning of the universe that might have allowed a single virtual particle to persist, to avoid annihilation, to become the seed of everything that followed? Some theorists suggest that in the extreme energies of the Big Bang, the usual rules were suspended. Particles and antiparticles were created in equal numbers, but somehow, through a process we still do not fully understand, a tiny asymmetry emerged. For every billion antiparticles, there were 1,000,000,001 particles. And when the universe cooled enough for matter and antimatter to annihilate each other, that tiny excess remained. One particle in 1,000,000,000 survived. And from that infinitesimal imbalance, everything, stars, planets, galaxies, life, eventually formed. The first particle, in this view, was not special because it was first, but because it was lucky. It was the survivor of a cosmic holocaust, a single fragment that escaped destruction and became the foundation of all that is. But there is a deeper problem, one that gnaws at the edges of every theory. If the vacuum can produce particles spontaneously, what produced the vacuum? If empty space has energy, where did that energy come from? If the quantum fields are fundamental, what made them fundamental? We have explained the first particle by invoking the vacuum, but we have not explained the vacuum itself. We have pushed the mystery back one layer, but we have not dispelled it. And some physicists have begun to suspect that this is not a flaw in our theories, but a feature of reality itself. Perhaps every explanation will always require a prior explanation. Perhaps the chain of causation extends backward infinitely, or loops back on itself, or terminates in something so far beyond our comprehension that we will never be able to grasp it. Perhaps the question, what created the vacuum, is unanswerable not because we lack knowledge, but because the question assumes a framework, time, space, causation, that breaks down at the deepest levels. Yet the universe itself does not seem troubled by these paradoxes. It exists, indifferent to our confusion. The vacuum continues to hum with virtual particles. The fields continue to oscillate. Matter continues to cohere into structures complex enough to ask these questions. And in that persistence, in that stubborn refusal to collapse into non-existence, there is something almost defiant. The universe does not owe us an explanation, and yet it provides one anyway, encoded in the behavior of particles, in the mathematics of fields, in the patterns we observe when we look closely enough. The first particle may have been a quantum fluctuation, or a phase transition, or a survivor of annihilation. But whatever it was the moment when possibility became actuality, when the restless energy of the vacuum crystallized into something we can touch and measure and name. And this is the unsettling beauty of quantum field theory. It tells us that creation is not a singular event, but a continuous process, happening everywhere, all the time. The vacuum is not the stage on which the play of existence unfolds. It is the play itself, endlessly improvising, endlessly generating new possibilities. Every cubic centimeter of empty space is a cauldron of potential, a field of energy waiting to express itself as matter. And if the first particle was simply the first instance of this process, then there is no true beginning at all. There is only the vacuum, doing what it has always done, what it will always do, for as long as time itself persists. The first particle was not the start of the story. It was the moment when the story became visible. But if nothing naturally produces something, if the vacuum is inherently generative, if empty space is the most fecund substrate imaginable, then we are left with a question that feels almost spiritual in its depth. What produced the nothing? What set the vacuum in motion? What established the fields, the laws, the mathematical structures that allow particles to emerge from emptiness in the first place? We have explained matter by invoking energy, energy by invoking fields, fields by invoking mathematics. But what invokes mathematics itself? What makes certain equations true and others false? What gives structure to the shapeless, pattern to the patternless, meaning to the meaningless? These are not scientific questions. They are metaphysical ones, and yet they hover over every attempt to understand the first particle, every theory of cosmic origins, every equation that tries to describe the transition from non-existence to existence. We are not just asking what created the first particle. We are asking what makes creation possible at all. And that question, perhaps, has no answer. Only echoes, reverberating through the void, forever. There is a moment in every creation myth where something breaks. In the Norse tradition, the giant Ymir is slaughtered and his body becomes the world, flesh to earth, blood to ocean, bones to mountains. In the Babylonian Enuma Elish, the goddess Tiamat is torn apart and her corpse fashioned into the heavens. Even in Genesis, creation begins with division, light from darkness, waters above from waters below, order carved from chaos. These stories, told across millennia and continents, seem to understand something fundamental about existence itself, that creation is not a process of building up from nothing, but of breaking apart from everything. That the universe does not emerge from emptiness, but from a kind of primordial wholeness that could not sustain itself. And here, in the mathematics of modern physics, we find the same pattern encoded in the fabric of reality. The first particle did not appear because something was added to the universe. It appeared because something was lost. Because a perfect symmetry, unable to hold itself together, shattered like frozen glass under its own weight. To understand this, we must first understand what physicists mean by symmetry. In everyday language, symmetry is about mirror images and balanced proportions, the left side matching the right, patterns repeating with elegant precision. But in physics, symmetry is something deeper and stranger. It is a statement about indifference, about equivalence, about the universe not caring which direction you're facing or which moment in time you occupy. If the laws of physics are the same everywhere and everywhen, then space and time possess a kind of symmetry. If electrons behave identically no matter how you rotate your laboratory, then the equations describing them possess rotational symmetry. And in the earliest moments of the universe, before particles had names, before forces had identities, there existed a symmetry so perfect, so complete, that nothing could be distinguished from anything else. There were no electrons, no quarks, no photons. There was only a kind of undifferentiated potential, a field of energy with no internal structure, no hierarchy, no preference for one state over another. It was everything and nothing simultaneously, a cosmic blank slate waiting for the first word to be written upon it. But perfect symmetry is unstable. This is one of the most profound and counterintuitive insights in modern physics. You might think that a perfectly balanced system would endure forever, that symmetry would be the most stable configuration imaginable. But the mathematics tells a different story. Imagine a ball balanced exactly at the peak of a hill. In principle, it could remain there indefinitely, poised in perfect equilibrium. But in practice, the slightest perturbation, a gust of wind, a tremor in the earth, a quantum fluctuation too small to measure, will send it rolling down one side or the other. And once it begins to fall, there is no going back. The symmetry is broken, and the ball will settle into a new state, one that is stable but no longer balanced. The universe, in its earliest moments, was like that ball. It existed in a state of perfect symmetry, perfect potential, perfect instability. And then something happened. Some tiny fluctuation, some quantum whisper, nudged it over the edge. And in that instant, everything changed. This process is called symmetry breaking, and it is responsible for nearly every feature of the universe we inhabit. In the first fraction of a second after the Big Bang, the universe was so hot, so dense, so energetic that all the fundamental forces, gravity, electromagnetism, the strong nuclear force, the weak nuclear force, were unified into a single superforce. There were no distinctions, no separations. A photon and a graviton were indistinguishable. An electron and a quark were the same thing. But as the universe expanded and cooled, this unified symmetry became unstable. The forces began to separate, to crystallize into distinct identities, like water freezing into ice or vapor condensing into droplets. First, gravity split off, then the strong nuclear force, then the electroweak force divided into electromagnetism and the weak force. And with each splitting, with each breaking of symmetry, new particles came into existence. The universe was not created all at once. It was created in stages, through a cascade of fractures, each one giving birth to new forms of matter and energy. But there is a deeper mystery here, one that haunts cosmologists and keeps them awake at night. When symmetry breaks, it usually produces matter and antimatter in equal amounts. For every electron that appears, a positron should appear. For every quark, an antiquark. And when matter meets antimatter, they annihilate each other in a burst of pure energy, leaving nothing behind. This is not speculation. We observe it in laboratories every day. Particle accelerators create matter-antimatter pairs, and they destroy each other instantly, converting their mass back into light. So if the early universe produced equal amounts of matter and antimatter, as the laws of physics suggest it should have, then everything should have annihilated everything else. The universe should have collapsed back into a featureless sea of radiation, a universe of light with no structure, no atoms, no stars, no planets, no life. And yet here we are. The universe is filled with matter. Galaxies exist. Stars burn. Atoms assemble into molecules. Something broke the symmetry between matter and antimatter. And we do not fully know what. This is called the baryon asymmetry problem, and it is one of the deepest unsolved puzzles in physics. The mathematics is unforgiving. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That tiny excess, 1 part in a billion, is everything. When the matter and antimatter annihilated, that single surviving particle out of every billion became the foundation of all material existence. Every atom in your body, every star in the sky, every grain of sand on every beach, traces its lineage back to that infinitesimal imbalance. But why? Why was there more matter than antimatter? What mechanism could have produced such a slight but critical asymmetry? Physicists have proposed several possibilities. Perhaps the laws of physics are not quite as symmetric as we thought. Perhaps certain particles decay in ways that favor matter over antimatter. Perhaps in the extreme conditions of the early universe, quantum effects introduced subtle biases. But none of these explanations are fully satisfying. None of them answer the deeper question: why does the universe prefer existence over non-existence? Why did it choose to be something rather than nothing? And this is where the story bends towards something almost spiritual, though it remains rooted in the mathematics of fields and forces. The Higgs mechanism, discovered experimentally in 2012, provides part of the answer. The Higgs field permeates all of space, and particles acquire mass by interacting with this field, like objects moving through honey. Before symmetry breaking, particles had no mass. They traveled at the speed of light, unable to cohere into stable structures. But when the Higgs field underwent its own symmetry breaking, when it settled into a non-zero value throughout the universe, particles began to slow down, to acquire mass, to become capable of binding together. The first particle was not just a fragment of matter appearing in empty space. It was a transformation, a moment when raw energy crystallized into something with weight, with persistence, with the capacity to endure. And this transformation was not instantaneous. It propagated outward, a wave of symmetry breaking that swept across the universe, turning potential into actuality, abstraction into substance. Yet the truth may be stranger than even this. Some theorists have proposed that symmetry breaking is not a one-time event, but an ongoing process, that the universe is constantly transitioning between different states of broken symmetry, and that what we perceive as stable reality is actually a kind of temporary equilibrium. Imagine the Higgs field not as a static background, but as a landscape of possibilities, with valleys and hills and peaks. The universe, in this view, is like a ball rolling through this landscape, and where it settles determines the properties of particles, the strengths of forces, the structure of physical law. But there is no guarantee that it will remain settled. If the universe occupies what is called a false vacuum, a valley that seems stable but is not the true lowest point, then eventually it could undergo another phase transition, another symmetry breaking, and the laws of physics themselves could change. Atoms might disintegrate. Forces might disappear. Reality as we know it could simply cease to be. This is not science fiction. It is a legitimate prediction of quantum field theory. And it suggests that the first particle was not the beginning of a story, but the middle, one episode in an endless series of transformations. But here a question emerges, one that feels almost too large to ask. If symmetry breaking created particles, what created the symmetry in the first place? What established the unified state from which everything fractured? We have explained the origin of particles by invoking broken symmetry, but we have not explained the origin of symmetry itself. And this leads us into territory where physics and philosophy become indistinguishable. Perhaps symmetry is not something that was created, but something that simply is, a mathematical truth that exists independent of the universe, like the axioms of geometry or the rules of logic. Or perhaps symmetry is an emergent property, something that arises from deeper structures we have not yet discovered. Or perhaps, and this is the most unsettling possibility, symmetry is an illusion, a pattern we impose on reality because our minds are built to detect patterns, and the true structure of existence is something we cannot perceive or comprehend. And this is where the dread sets in, the existential vertigo that comes from realizing how fragile the entire edifice of existence truly is. The universe did not have to be this way. The symmetry could have broken differently. The Higgs field could have settled into a different configuration. The imbalance between matter and antimatter could have been slightly smaller, and everything would have annihilated. Or slightly larger, and the universe would have evolved in ways we cannot imagine. We are living in one of countless possible outcomes, and there is no reason, no physical, mathematical, or logical necessity why it had to be this one. The first particle was an accident, or a choice, or a consequence of laws we do not understand. And everything that followed, every star, every thought, every moment of love or suffering or wonder, rests on that initial contingency. We are not inevitable. We are not necessary. We are the descendants of a cosmic flaw, a broken symmetry, a moment when the universe could not hold itself together and fractured into the shapes we now call reality. Yet there is wonder here too, a kind of awe that transcends the mathematics. Because if the universe is built on broken symmetry, then imperfection is not a bug, but a feature. The cracks are not flaws. They are the structure itself. And perhaps this is the deepest truth the first particle teaches us. That creation requires destruction, that order requires chaos, that existence requires the willingness to shatter what came before. The ancient myths understood this. The Norse saw the world born from violence. The Babylonians saw creation as conquest. Even the Christian tradition speaks of the word breaking the silence, light rupturing the darkness. And now modern physics confirms it in the language of fields and phase transitions and spontaneous symmetry breaking. The first particle did not emerge from nothing. It emerged from everything, from a totality so complete it could not sustain itself. And in breaking apart, it became the foundation of all that is. But if particles emerged from broken symmetry, if the universe is the product of a phase transition, if reality itself is a kind of crystallization of potential into actuality, then we are left with the most haunting question of all. Who, or what, broke the symmetry? Was it a random quantum fluctuation, a purposeless jitter in the fabric of existence? Was it an inevitability, a mathematical necessity encoded in the structure of fields and forces? Or was it something else, something we have no language for, something that stands outside the categories of chance and necessity entirely? The universe does not answer. It only shows us the aftermath, the fragments, the particles that remain. And in those fragments, we try to reconstruct the moment of breaking, the instant when wholeness became multiplicity, when unity became diversity, when nothing became something. But the moment itself remains hidden, obscured by the limits of our instruments and the boundaries of our understanding. We can measure the particles. We can map the forces. We can write equations that describe how symmetry breaks and what emerges from the breaking. But we cannot see the breaking itself. We cannot witness the moment when the first particle came into being. We can only stand in the present and look backward, tracing the consequences, following the threads, trying to imagine what it must have been like when everything was about to begin. There is a thought that, once encountered, refuses to leave. It sits at the edge of consciousness like a half-remembered dream, unsettling and luminous. The thought is this: what if the first particle never existed at all? What if everything we call matter, the atoms in our bodies, the stars in the sky, the ground beneath our feet, is not really made of particles, but of something stranger, something more abstract, something that exists in a realm so far removed from everyday experience that calling it real feels almost like a category error? This is not mysticism. This is not metaphor. This is the direction that fundamental physics has been pointing for decades, and the implications are so disorienting that even physicists struggle to hold them clearly in mind. Because if particles are not fundamental, if they are merely patterns, vibrations, disturbances in something deeper, then the question of the first particle dissolves. It becomes like asking about the first wave in an ocean that has always existed, or the first note in a symphony that has no beginning. And we are left standing on the shore of reality, realizing that everything we thought was solid is actually just movement, just rhythm, just the universe playing itself like an instrument we cannot see. This insight begins with quantum field theory, but it does not end there. We have already seen that particles emerge from fields, that electrons and quarks and photons are excitations in invisible structures that fill all of space. But this raises an immediate question. What are the fields themselves? Are they made of something? Do they rest on a substrate? Or are they the substrate? And if they are fundamental, why are there so many of them? One for electrons, one for quarks, one for every type of particle we observe. The proliferation seems arbitrary, inelegant, as if nature is using too many ingredients when a simpler recipe should suffice. And this is where string theory enters, not as a definitive answer, but as a radical reconceptualization of what it means for something to exist. String theory proposes that particles are not point-like objects, but tiny, vibrating loops of energy, strings so small that even our most powerful instruments cannot resolve them. And the different particles we observe, electrons, quarks, photons, are simply different vibrational modes of the same fundamental string, like different notes played on the same cosmic guitar. If this is true, and we do not yet know if it is, then the first particle was not a thing that appeared, but a vibration that began. Imagine a string, infinitesimally small, existing in a space where space itself has not yet fully formed. The string begins to oscillate, and the pattern of its oscillation determines what kind of particle it appears to be. A certain frequency produces an electron. Another produces a quark. Another produces a photon. The particle is not separate from the vibration. It is the vibration, a temporary configuration of energy that persists only as long as the string continues to move. And if the string stops vibrating, the particle vanishes, dissolving back into the formless potential from which it came. In this picture, matter is not substance but music, not object but process, not being but becoming. And the first particle was the first note in a composition that has been playing ever since, a melody that has grown so complex, so layered, so rich with harmonics that we have mistaken it for a solid, stable, material world. But string theory goes further, and this is where the vertigo truly begins. The mathematics of strings only works, only remains consistent with the known laws of physics, if space has more than 3 dimensions, not just the 3 we experience, length, width, height, but additional dimensions, perhaps 6 or 7 or even more, curled up so tightly that they are invisible, folded into structures smaller than atoms, smaller than nuclei, smaller than anything we can measure. And in these hidden dimensions, the strings vibrate in ways that determine not just the types of particles but the strengths of forces, the values of constants, the entire architecture of physical law. The universe we inhabit, in this view, is like a shadow cast by a higher dimensional reality, a projection onto the 3-dimensional surface of something far more intricate and strange. And particles are not objects moving through space, but patterns encoded in the geometry of dimensions we cannot see. This is not easy to accept. Every instinct we have, every lesson learned from a lifetime of navigating the physical world, tells us that matter is real, that particles are things, that space is a container, and time is a progression. But physics has been chipping away at these intuitions for over a century, and what remains is something almost unrecognizable. Einstein showed us that space and time are not separate but woven together, that they bend and stretch in the presence of mass and energy. Quantum mechanics showed us that particles are also waves, that they exist in states of superposition, that observation itself alters what is observed. And now string theory and its successor, M theory, suggest that even space-time itself may not be fundamental. It may be emergent, a phenomenon that arises from deeper structures, the way wetness emerges from the collective behavior of water molecules or temperature emerges from the motion of atoms. Space-time, in this view, is not the stage on which the cosmic play unfolds. It is part of the play, a character that only appears when certain conditions are met. And this is where the loneliness sets in, the existential chill that comes from realizing how far removed we are from the foundations of existence. We are not living in the real universe. We are living in a projection, a shadow, a surface phenomenon. The true structure of reality exists in dimensions we cannot access, described by mathematics we can barely understand, governed by principles that have no analog in everyday experience. And particles, those tiny, discrete, seemingly solid building blocks of matter, are just ripples on the surface, disturbances in a deeper ocean, echoes of vibrations occurring in spaces we will never see. Every atom in your body, every photon entering your eye, every neuron firing in your brain is a kind of illusion, a pattern mistaken for a thing, a process mistaken for an object. You are not made of matter. You are made of music, and the musician is invisible. But there is another possibility, one that pushes even further into abstraction. Some physicists have begun to explore the idea that reality is not built from strings or fields or particles at all, but from information. In this view, the universe is fundamentally computational, a vast network of relationships and correlations, and what we call matter is simply a way of organizing information into stable patterns. A particle is not a physical object, but a knot in the web of information, a place where data converges and persists. And the first particle was not an event in space and time, but an event in the space of possibilities, a moment when information crystallized into a form that could be measured, observed, named. This is not science fiction. It emerges naturally from the study of black holes, from the holographic principle, from attempts to reconcile quantum mechanics with general relativity. And it suggests that the question of the first particle is not about when or where or how, but about what it means for information to exist, to persist, to take on the appearance of substance. Yet the truth may be stranger than any of these options. M-theory, the most ambitious attempt to unify all of physics, proposes that strings are not the deepest layer of reality, but are themselves emergent from something called brains, multidimensional membranes that float in an 11-dimensional space. Our entire universe, in this picture, might be a 3-dimensional brain embedded in a higher dimensional bulk, and particles are the result of brains colliding, intersecting, vibrating against each other. The first particle, then, was not an object that appeared within our universe, but a consequence of our universe coming into contact with something outside itself. And if this is true, then the origin of matter is not a question about what happened inside space-time, but about what caused space-time to form in the first place. We are asking the wrong question. We are looking for the first particle when we should be asking about the first intersection, the first collision, the first moment when separate realms of existence touched and produced the phenomenon we call reality. And this is the deepest mystery, the one that all these theories circle without quite touching. If particles are vibrations in fields, and fields are excitations of space-time, and space-time is emergent from higher dimensions or information or brains, then what is fundamental? What lies at the bottom? What is the bedrock on which everything else rests? Some physicists believe there is no bedrock, that reality is turtles all the way down, an infinite regress of structures emerging from structures. Others believe that we simply have not yet discovered the deepest layer, that there is some ultimate substrate, some final equation, some primordial entity that gives rise to everything else. And still others suggest that the question itself is malformed, that asking what is fundamental is like asking what direction is north of the North Pole. It assumes a hierarchy that may not exist. It assumes that reality is built from parts when reality might be a seamless whole, indivisible and irreducible. But here a question emerges, one that feels almost too large to contemplate. If particles are just vibrations in deeper structures, who or what tuned the first vibration? Who set the strings in motion? Who determined the frequency, the amplitude, the pattern of oscillation that would produce an electron rather than a quark, a photon rather than a graviton? In music, every note requires a musician. In waves, every ripple requires a disturbance. And if the universe is fundamentally vibrational, then something must have initiated the vibration, must have plucked the cosmic string, must have set the fields into motion. But what? A random quantum fluctuation? A necessary consequence of mathematical structure? Or something else entirely? Something that stands outside the categories of cause and effect, necessity and chance, being and non-being? The universe does not answer. It only shows us the patterns, the vibrations, the particles that emerge from deeper structures. And in those patterns, we try to read the signature of whatever initiated them, whatever set the first string vibrating, whatever caused information to coalesce into the forms we recognize as matter and energy. But the initiation itself remains hidden, veiled behind layers of abstraction, obscured by the limits of our instruments and the boundaries of our mathematics. We can measure the vibrations. We can map the patterns. We can write equations that describe how strings oscillate and what particles emerge from those oscillations. But we cannot see the moment when the first vibration began. We cannot witness the instant when the first note was played. We can only stand in the present and listen to the music, trying to reconstruct the composition, trying to imagine what the opening chord must have sounded like when everything was about to begin. And this is where the cosmic loneliness becomes almost unbearable. Because if we are surface phenomena, if we are shadows cast by higher dimensional structures, if we are patterns of information mistaking ourselves for substance, then we are profoundly disconnected from the true nature of reality. We will never see the deeper dimensions. We will never touch the fundamental strings. We will never step outside space-time and observe it from the outside. We are imprisoned within our own existence, confined to a three-dimensional slice of a much larger reality, and everything we experience, every sensation, every thought, every moment of awareness, is filtered through the limitations of our dimensional confinement. The real universe, the one where particles are born, where fields originate, where the first vibration was tuned, exists in a space we cannot access. And we are left here, in the shadows, trying to deduce the shape of the light that casts us. Yet there is something defiant in our attempts to understand, something almost heroic in the refusal to accept the surface as the totality. We know we are shadows, and yet we reach toward the light. We know we are trapped in three dimensions, and yet we construct mathematics that describes dimensions we cannot see. We know particles might be illusions, and yet we build instruments to measure them with ever greater precision, as if by understanding the illusion thoroughly enough we might glimpse the reality beneath. And perhaps this is what it means to be conscious, to be aware, to be a fragment of the universe that has somehow learned to question its own nature. We are the music trying to understand the musician. We are the vibration attempting to comprehend the string. We are the shadow reaching back toward the substance that cast it. And in that reaching, in that striving, in that restless need to know, we are participating in something profound. We are the universe's attempt to know itself, even if that knowledge will always be partial, incomplete, filtered through layers of emergence and abstraction. And so the first particle remains elusive, not because we lack the tools to find it, but because it may not exist in the way we imagine. It was not a thing that appeared. It was not an object that emerged from nothing. It was a pattern, a vibration, a note played on an instrument we cannot see. And we are the echoes of that note, reverberating through dimensions, propagating through time, creating the illusion of solidity and substance and separateness. The first particle was never a particle at all. It was the first moment when the universe learned to sing. There is a crack in the foundation of every creation story ever told, a fault line so fundamental that once you see it, you cannot unsee it. Every myth, every religion, every scientific theory that tries to explain the origin of the universe makes the same implicit assumption: that time already exists, that there is a before and an after, a moment when nothing existed followed by a moment when something did. We speak of the Big Bang as an event that happened 13.8 billion years ago, as if years ago means something absolute, as if time is a river that has always been flowing and we are simply asking where it begins. But what if this assumption is wrong? What if time itself is not fundamental but emergent, not a stage on which events unfold, but a consequence of those events? What if asking what came before the first particle is like asking what is north of the North Pole? A question that sounds meaningful but collapses into incoherence the moment you examine it closely. Because if time did not exist in the earliest moments, if there was no before the Big Bang, then the entire concept of creation becomes paradoxical. How can something be created if there is no time in which creation can occur? How can a cause precede an effect if precedence itself has no meaning? This is not a new problem. Augustine of Hippo grappled with it in the 4th century, arguing that God created time along with the universe, and therefore asking what God was doing before creation is nonsensical. There was no before. But Augustine was working with theology, not physics, and his solution rested on faith rather than mathematics. Modern physics has arrived at the same conclusion through a completely different route, and the implications are far stranger than Augustine could have imagined. Einstein's theory of general relativity showed us that time is not absolute, that it can stretch and compress, that it runs at different rates depending on how fast you are moving or how deep you are in a gravitational field. Near a black hole, time slows to a crawl. At the event horizon, it stops altogether. And if time can stop, if it can vary, if it is not a fixed backdrop, but a dynamic, flexible dimension woven into the fabric of space-time itself, then it is not hard to imagine scenarios where time simply does not exist, where the universe exists in a state that has no temporal dimension at all. This is where the concept of the block universe enters, and it is one of the most disorienting ideas in all of physics. In our everyday experience, time flows. The past is gone, the future has not yet arrived, and only the present is real. But relativity tells a different story. It suggests that past, present, and future all exist simultaneously, laid out like frames in a film strip, and what we call the flow of time is simply our consciousness moving through this static structure, illuminating one moment after another. In the block universe, the first particle does not come into existence at a particular moment. It simply exists, eternally present, at a particular location in four-dimensional space-time. There is no creation event, no moment of transition from non-existence to existence. There is only the entirety of space-time, containing everything that has ever happened or will ever happen, and our perception of time is an illusion generated by the way our brains process information. The first particle was always there, will always be there, existing in a timeless now that encompasses the entire history of the cosmos. But this raises an immediate question. If the block universe is real, if past and future are equally existent, then what explains the arrow of time? Why do we remember the past, but not the future? Why does entropy increase, disorder spread, structures decay? Why does time seem to have a direction when the fundamental equations of physics are time-symmetric, working equally well whether time runs forward or backward? The answer may lie in quantum mechanics, in the process of measurement and observation, in the collapse of wave functions that seems to introduce an irreversible element into the evolution of the universe. Or it may lie in cosmology, in the low-entropy state of the early universe, a state so improbable, so finely tuned, that everything since has been a gradual slide toward equilibrium. But these are not explanations. They are descriptions of the arrow's consequences, not its cause. And they do not resolve the deeper mystery. If time is emergent, if it arises from something more fundamental, then what is that something? What gives birth to time itself? One possibility, strange and elegant, comes from the study of quantum entanglement. When two particles become entangled, Their states are linked in such a way that measuring one instantly affects the other, regardless of the distance separating them. Einstein called this spooky action at a distance and was deeply troubled by it, but experiments have confirmed it beyond any doubt. And some physicists have begun to suspect that entanglement is not just a feature of quantum mechanics, but the very fabric from which spacetime is woven. In this view, time does not exist at the most fundamental level. What exists is a vast network of quantum correlations, particles connected to other particles in an intricate web of relationships. And time emerges from the pattern of these correlations, from the way information flows through the network, from the accumulation of entanglement as the universe evolves. The first particle, in this picture, did not appear at a moment in time. It appeared as part of the process that created time itself, a node in the network whose existence is inseparable from the temporal structure it helped to generate. But there is another possibility, one that dissolves the problem of origins in a completely different way. What if the universe has no beginning at all? What if it is cyclic, eternally oscillating between expansion and contraction, Big Bang followed by Big Crunch followed by Big Bang again, in an endless rhythm that has no start and no end? In cyclic cosmology, the first particle is not the first particle ever. It is simply the first particle of this cycle, and there were infinite particles before it in previous cycles, and there will be infinite particles after it in cycles yet to come. Time, in this model, is not a line extending from a beginning to an end, but a circle, or perhaps a spiral, repeating with variation, each cycle slightly different from the last. And the question of what created the first particle dissolves, because there is no first. There is only the eternal recurrence, the universe playing itself over and over, a cosmic loop that needs no explanation beyond its own existence. Yet even this does not escape the deeper paradox. Because if the universe is cyclic, what sustains the cycles? What prevents the universe from simply stopping, from collapsing into a final, permanent state of maximum entropy? And if each cycle is slightly different, what determines the variations? What introduces novelty into the pattern? We have not eliminated the mystery of origins. We have only displaced it, moved it from the beginning of time to the structure of time itself. And we are still left with the question, why does time exist at all? Why is there temporal structure rather than timeless stasis? Why does the universe unfold, evolve, change, rather than simply being, frozen and eternal, in a single unchanging configuration? And this is where the existential dread intensifies, where the ground beneath our conceptual feet begins to crumble. Because if time is emergent, if it does not exist at the most fundamental level, then causality itself is an illusion. Cause and effect, the principle that underlies all of our reasoning, all of our science, all of our ability to navigate the world, is a feature of the temporal universe, but not a feature of the timeless reality from which it emerges. In the timeless realm, there is no before and after. There is no sequence. There is no progression. There is only a vast, static pattern, a mathematical structure that contains within itself all possible states, all possible configurations, all possible histories. And what we experience as the flow of time, as the unfolding of events, is simply our consciousness tracing a path through this timeless landscape, a path that happens to have a temporal structure because that is what consciousness requires to function. But here a question emerges, one that feels almost unbearable in its implications. Can something be created in the absence of a before? Can there be a first particle if there is no moment that precedes it, no time in which it does not exist followed by a time in which it does? Our intuition screams no. Creation requires a transition, and transitions require time. But physics suggests that our intuition is wrong, that it is possible for something to exist without having been created, for a state to be initial without being preceded. The Big Bang, in this view, is not an event that happened within time, but the event that created time, and asking what happened before it is like asking what temperature is colder than absolute zero. The question is grammatically correct, but physically meaningless. The first particle did not come into existence at a moment in time. It came into existence along with time itself, as part of the very fabric of temporal structure. And this leads to a possibility so strange that even physicists hesitate to articulate it clearly. What if the past is not fixed? What if quantum mechanics applies not just to particles and atoms, but to the entire history of the universe, including its origin? In standard quantum mechanics, a particle does not have a definite position until it is measured. Before measurement, it exists in a superposition of all possible positions, and the act of observation collapses this superposition into a single outcome. But some interpretations of quantum mechanics, particularly the Wheeler-DeWitt equation in quantum cosmology, suggest that the same principle applies to the universe as a whole. The universe does not have a single, definite history. It has many possible histories, existing in superposition, and what we call the past is simply the history that is consistent with our current observations. The first particle, in this view, does not have a definite origin. It has many possible origins, and which one is real depends on what we observe now, in the present. The past, in a very real sense, is being created by the present, and the first particle is not something that happened 13.8 billion years ago, but something that is happening now. Every time we measure something, every time we observe something, every time we collapse a wave function and force the universe to choose a history. This is not easy to accept. It violates every intuition we have about time, about causality, about the fixedness of the past. But it emerges naturally from the mathematics of quantum mechanics, and some experiments, particularly those involving delayed choice setups, seem to confirm it. A photon can be forced to choose whether it behaved as a wave or a particle in the past based on measurements made in the present. The present affects the past, or perhaps more accurately, the present determines which past is actualized from the superposition of possible pasts. And if this applies to photons, why not to the entire universe? Why not to the Big Bang itself? Why not to the first particle? Perhaps there is no single, definite moment when the first particle came into existence. Perhaps there are many such moments, existing in quantum superposition, and our observations in the present are constantly collapsing that superposition, constantly choosing which origin story is real. Yet the truth may be stranger still. Some physicists have proposed that time is not just emergent but approximate, that it is a useful fiction at large scales, but breaks down completely at the smallest scales. At the Planck scale, the smallest possible length, about 10⁻35 meters, and the smallest possible time, about 10 to 43 seconds, the smooth fabric of space-time dissolves into a quantum foam, a seething chaos of virtual black holes and wormholes and fluctuations so violent that the very concepts of distance and duration lose meaning. And if time breaks down at the Planck scale, then the first particle cannot have emerged at a specific Planck moment, because Planck moments do not exist as discrete, well-defined intervals. Time, at that scale, is not a sequence but a blur, a quantum smear, a phenomenon that has not yet crystallized into the clear, linear structure we experience at macroscopic scales. The first particle, in this picture, did not appear at a moment in time, but emerged gradually as time itself congealed from the quantum foam, as the universe transitioned from a timeless, spaceless state into one where space-time could exist. And this is the deepest mystery, the one that haunts every attempt to understand the origin of the universe. If time is emergent, if it arises from quantum entanglement or space-time geometry or some deeper structure we have not yet discovered, then the question of the first particle is not a question about what happened at a particular moment, but a question about how temporal structure itself came to be. We are not asking when the first particle appeared. We are asking how, when became possible. We are asking how the universe transitioned from a state where time did not exist, where before and after had no meaning, where causality was not yet a concept, into a state where time flows, where events unfold in sequence, where the past is fixed and the future is open. And this transition, if it happened at all, is not something we can observe directly. It is not something that left traces we can measure. It is the precondition for all observation, all measurement, all trace leaving. It is the moment when the universe became the kind of place where moments could exist. And so we are left suspended, floating in a conceptual void where the usual anchors of understanding have dissolved. The first particle may not have been first because there was no time in which it could be first. It may not have been created because creation requires a before and there was no before. It may exist in a timeless now that encompasses all of history, or in a superposition of possible pasts that collapse into actuality only when observed, or in a cyclic pattern that repeats without beginning or end. The universe does not owe us a narrative. It does not owe us a story with a clear beginning, middle, and end. And perhaps the deepest lesson of modern physics is this: that the universe is under no obligation to make sense to creatures like us, evolved to navigate 3 spatial dimensions and 1 dimension of time, creatures whose brains are built to detect patterns and impose order and demand explanations. The first particle, if it existed at all, existed in a realm where our concepts do not apply, where time had not yet become time, where being and becoming had not yet separated. And we can reach toward that realm with mathematics and imagination, but we can never fully enter it. We can only stand at the boundary, looking back toward a moment that may not have been a moment at all, trying to understand how something, everything, came from a timelessness we can barely conceive. There is a concept in logic called a strange loop, a hierarchy that folds back on itself in such a way that moving upward through the levels eventually brings you back to where you started. Escher drew them as impossible staircases. Gödel discovered them in the foundations of mathematics. And now physicists are beginning to suspect that the universe itself might be the ultimate strange loop, a system that creates the conditions for its own existence, a cosmos that bootstraps itself into being without requiring anything external, anything prior, anything beyond itself. This is not mysticism. This is not philosophical speculation divorced from evidence. This is a direct consequence of quantum mechanics and general relativity, a prediction that emerges when you take the equations seriously and follow them to their logical conclusion. The universe, it seems, may not have been created at all. It may have simply decided to exist, a self-contained loop of causation that needs no beginning because it is its own beginning, no creator because it is its own creator, no first particle because the very structure of physical law makes existence not just possible, but inevitable. The idea sounds absurd, a violation of everything we know about causation and contingency. In our everyday experience, nothing creates itself. Buildings require architects. Paintings require painters. Even thoughts require brains. The chain of causation always extends backward, effect following cause, until we reach something that seems to require an explanation outside the system. But quantum mechanics has been teaching us for a century that our everyday intuitions are poor guides to reality, and nowhere is this more apparent than in the question of origins. Because quantum mechanics allows something that classical physics forbids, the spontaneous appearance of particles from apparently nothing, a phenomenon called quantum tunneling. A particle can pass through a barrier even if it lacks the energy to climb over it, not by violating conservation laws, but by borrowing energy from the vacuum for such a brief moment that the universe's accounting system never quite catches the violation. And if a particle can tunnel through a barrier, can a universe tunnel through the barrier between non-existence and existence? This is the question that Alexander Vilenkin asked in the early 1980s, and his answer was astonishing. Yes, a universe can tunnel into existence from literally nothing, not from a pre-existing vacuum or quantum field, but from absolute nothingness. No space, no time, no energy, no laws. The mathematics of quantum cosmology, when applied to the very earliest moments, suggests that a universe can spontaneously nucleate, like a bubble forming in boiling water, except the bubble is space-time itself, and the water is nothing. Not a quantum foam, not a pre-geometric structure, just nothing. And the probability of this happening is not zero. It is small, infinitesimally small, but in a timeless void where nothing can happen, even infinitesimal probabilities become inevitable because there is no time constraint, no deadline by which the event must occur or fail to occur. If something has any probability of happening and infinite time is available, then it must happen. And if time does not exist outside the universe, then infinite time is replaced by something even stranger, a kind of timeless probability space where all possible events exist simultaneously, and the universe we inhabit is simply one that happened to cross the threshold from possibility to actuality. But here a deeper question emerges, one that Vilenkin himself struggled with. If the universe tunneled from nothing, what provided the quantum mechanical framework in which tunneling could occur? Quantum mechanics is a set of laws, a mathematical structure, and structures seem to require some kind of existence. How can laws operate in the absence of anything for them to operate on? Vilenkin's answer is that the laws of physics are not contingent. They are necessary truths, like the axioms of mathematics, existing independent of any physical instantiation. The universe did not create the laws. The laws are eternal, timeless, and the universe is simply one possible solution to those laws, one configuration that happens to satisfy the equations. But this raises an immediate objection. Why these laws and not others? Why quantum mechanics and general relativity? Why not some completely different set of principles? And if the laws themselves require an explanation, have we really eliminated the need for a first cause, or have we simply moved it from the universe to the laws that govern it? Stephen Hawking approached the same question from a different angle, and his answer was even more radical. In his final book, written with Leonard Mlodinow, Hawking argued that the universe does not need a cause because causation itself is a concept that only applies within the universe, not to the universe as a whole. Asking what caused the Big Bang is like asking what is south of the South Pole. The question assumes a framework that breaks down at the boundary. Time, according to Hawking, does not extend infinitely into the past. It has a beginning, but that beginning is not a moment in time. It is a boundary in space-time, a point where the normal rules of causation cease to apply. And near that boundary, space-time becomes Euclidean rather than Lorentzian, which is a technical way of saying that the dimension we call time becomes indistinguishable from the dimensions we call space. There is no before the Big Bang because before requires time, and time does not exist outside the universe. The universe is self-contained, needing no external cause, no external creator, no first particle introduced from outside. It simply is a closed loop in space-time, a system that creates the conditions for its own existence. Yet even this does not quite capture the strangeness of what modern cosmology is suggesting. Because it is not just that the universe might have created itself, but that it might have been inevitable, not contingent, not one possibility among many, but necessary, the only possible outcome given the structure of physical law. This is the implication of the no-boundary proposal, developed by Hawking and James Hartle, which suggests that the universe has no initial boundary in time, no moment of creation, but instead a smooth geometry that curves back on itself. In this picture, asking what came before the Big Bang is like asking what lies north of the North Pole. The question is grammatically correct, but conceptually meaningless, because north ceases to have meaning at the pole itself. And if the universe has no boundary, no beginning, then it does not need to be created. It simply exists, and its existence is a consequence of the mathematical structure of space-time itself. But not all physicists agree. Roger Penrose, one of the most respected voices in cosmology, has argued forcefully that the Big Bang was not a self-contained event, but part of a larger structure, a cyclic cosmology in which each universe gives birth to the next through a process he calls conformal cyclic cosmology. In Penrose's model, the universe does not begin with a singularity, but emerges from the far future of a previous universe, a future in which all matter has decayed, all black holes have evaporated, and only massless particles remain. And in the absence of matter, time loses its meaning, and the infinite future of the old universe becomes the Big Bang of the new. The first particle of our universe was not created from nothing. It was inherited from the final state of the universe that preceded ours. And this process repeats eternally, each cycle leaving subtle imprints on the cosmic microwave background, faint echoes of collisions between black holes in the previous aeon. Penrose claims to have found evidence of these echoes, though the physics community remains divided on whether the signals are real or statistical artifacts. And then there is Alan Goose's theory of cosmic inflation, which proposes that the universe underwent a period of exponential expansion in the first fraction of a second, driven by a scalar field in a high-energy state. Inflation solves many problems in cosmology. It explains why the universe is so uniform, why it is flat, why we do not observe magnetic monopoles. But it also introduces a new mystery. What created the inflating field? Where did the energy for inflation come from? Goose's answer is elegant and unsettling. The energy came from nothing. Inflation is a mechanism by which gravity, normally an attractive force, becomes repulsive, and in doing so it creates matter and energy out of the gravitational field itself. The universe, in this picture, is a kind of perpetual motion machine, generating its own fuel as it expands. And once inflation starts, it never completely stops. It creates bubble universes, pocket universes, each with its own laws of physics, each inflating eternally, creating an infinite multiverse of which our observable universe is just one infinitesimal fragment. The first particle of our universe was not the first particle in existence. It was one of an infinite number of first particles, each appearing in its own bubble, each marking the beginning of a new cosmos. But there is a deeper problem here, one that gnaws at every attempt to explain the universe's self-creation. If the universe created itself, if it bootstrapped itself into existence through quantum tunneling or inflation or cyclic recurrence, then it still requires something: the laws of physics themselves. Quantum mechanics must already exist for quantum tunneling to occur. The inflating field must already exist for inflation to happen. The structure of space-time must already exist for conformal cyclic cosmology to operate. And these are not nothing. They are something, and that something demands an explanation. Why do these laws exist rather than others? Why do they have the specific mathematical form they have? Why do they permit self-creation at all? Some physicists argue that the laws are necessary, that they could not have been otherwise, that there is only one consistent set of laws, and we are simply discovering them rather than inventing them. But this is a metaphysical claim, not a physical one, and it is far from clear that it is true. Other sets of laws seem perfectly consistent, at least in the abstract. Universes with different numbers of dimensions, different forces, different particles, can be described mathematically. Why did reality choose these laws and not those? And this is where the tension between competing models becomes almost unbearable. Vilenkin says the universe tunneled from nothing. Hawking says it has no boundary. Penrose says it emerged from a previous cycle. Goose says it inflated from a quantum fluctuation. Linda says there is an eternal multiverse of inflating bubbles. And each of these models is mathematically rigorous. Each is consistent with what we observe, and each is fundamentally incompatible with the others. They cannot all be true. But we lack the experimental evidence to distinguish between them. We cannot observe the moment of the Big Bang directly. We cannot see beyond the cosmic horizon. We cannot access other universes if they exist. And so we are left with a proliferation of theories, each elegant, each compelling, each offering a different answer to the question of how the universe created itself, or whether it needed to be created at all. Yet there is something almost beautiful in this proliferation, something that hints at a deeper truth. All of these theories, despite their differences, converge on a single astonishing claim: that existence does not require permission, that the universe does not need an external creator, an external cause, an external spark to bring it into being, that the laws of physics, whatever they are sufficient to generate reality from their own internal structure. The first particle, in all of these models, was not introduced from outside. It emerged from within, from the mathematical structure of possibility itself. And if this is true, then the question of the first particle is not about what happened at a particular moment, but about why the laws of physics permit anything to happen at all. Why is there a framework in which universes can exist? Why is there mathematics? Why is there structure rather than formlessness, pattern rather than chaos, being rather than non-being? And here we arrive at the most unsettling possibility of all, that the universe is its own origin not because it created itself in time, but because it exists outside of time as a necessary consequence of logical structure. In this view, the universe is not a thing that came into existence, but a truth that could not fail to be true, a solution to an equation that could not remain unsolved. The first particle was not created. It was inevitable, a necessary consequence of the fact that certain mathematical structures cannot help but instantiate themselves, cannot help but become real. This is the Platonic view, the idea that mathematical truths exist independent of physical reality, and that physical reality is simply the manifestation of those truths, the way a symphony is the manifestation of a musical score. The universe does not need a composer because the score itself is self-playing, self-executing, self-realizing. But this is not a satisfying answer. It is a relabeling of the mystery, a shifting of the question from "why does the universe exist?" to "why does mathematics exist?" And we are no closer to a resolution. We have only pushed the problem back one layer, from the physical to the abstract, from matter to structure, from being to form. And at every layer, the same question recurs: why this and not nothing? Why structure rather than void? Why existence rather than non-existence? The universe may have created itself, but the capacity for self-creation is itself something that requires explanation. And we do not have one. We may never have one. Because the question may be unanswerable, not due to a lack of evidence, but due to a fundamental limitation in what questions can achieve. We are asking existence to justify itself, and existence does not owe us a justification. And so we are left standing at the edge of the knowable, looking back at the moment. If it was a moment, when the universe came into being, or always was, or created itself, or emerged from a previous cycle, or tunneled from nothing, or inflated from a fluctuation. Each theory is a lens, and through each lens the first particle looks different: a quantum fluctuation, a boundary condition, a vibrational mode, a necessary consequence, an inherited remnant, a self-caused event. And perhaps the truth is that all of these perspectives are partial, each capturing one facet of a reality too vast, too strange, too self-referential to be contained in a single narrative. The first particle may have been all of these things at once, or none of them, or something we have not yet imagined. But what is clear is that the universe, however it began, did not require a creator standing outside it, reaching in to set things in motion. The universe is its own origin, its own cause, its own explanation. And in that self-sufficiency, in that strange loop of existence creating the conditions for its own existence, there is something deeply mysterious and deeply beautiful. The cosmos is not a machine that needed to be started. It is a process that never needed to begin because it never was not happening. And the first particle, if it existed at all, was simply the first moment when that eternal process became visible, measurable, knowable to creatures like us who exist within it, asking questions about it, trying to understand how something can come from nothing or everything from itself. Before the first particle, there was something else, something that defies the very language we use to describe matter. To speak of particles is to assume structure, boundaries, identity. But in the earliest moments, none of these existed. The universe was not filled with things. It was filled with potential, raw, seething, formless potential that had not yet collapsed into the discrete units we now call particles. This was the age of the inflating field, a hypothetical state of pure energy that preceded everything familiar. Not matter, not light, not even empty space as we understand it. Just a field, stretched taut across dimensions we cannot see, vibrating with an intensity that would soon ignite existence itself. The inflaton was not a particle. It was a condition, a background hum that permeated all of reality before reality had taken shape. Some theories describe it as a scalar field, smooth and featureless, with no directional properties, no spin, no charge. It simply was. And yet, within this simplicity lay a paradox. The inflaton carried energy, and energy warps spacetime. So even in this pre-particle phase, geometry was already bending, already preparing for the explosive moment when potential would become actual. But here a question emerges. If the inflaton was not made of particles, what was it made of? And if it was a field, what was the field resting upon? To answer this, we must descend deeper, below the threshold where classical physics dissolves, into the Planck scale, where distance becomes meaningless and time stutters. At this scale, spacetime itself is not smooth. It is foam, quantum foam, a churning, probabilistic froth where the fabric of reality boils with virtual particles that flash in and out of existence faster than anything can measure. Here, geometry is not a stage upon which events unfold. Geometry is the event. It twists, splits, reconnects, forming temporary wormholes and microcosmic bridges that collapse before they can stabilize. This is not a place. It is a condition of radical instability, where the laws that govern particles, conservation, causality, identity, have not yet taken hold. And yet, even this foam must rest on something. Perhaps it rests on a pregeometric phase, a state so primordial that even the notion of dimension is provisional. Some models propose that space-time itself emerged from a more fundamental substrate, a network of quantum information, or a lattice of abstract relations that only later crystallized into the 3 dimensions of space and 1 dimension of time we experience. In this view, the universe before particles was not spatial at all. It was logical. It was combinatorial. It was a web of correlations waiting to collapse into coordinates. But there is a deeper problem: energy density. At the earliest moments, the energy density of the universe was so extreme that matter as we know it could not exist. The temperatures were beyond the reach of any particle accelerator we have ever built or will ever build. Quarks could not bind. Electrons could not orbit. Even the fundamental forces, electromagnetism, the strong and weak nuclear forces, gravity, had not yet separated into distinct identities. They were unified, a single superforce governing a universe too hot and dense for differentiation. In this crucible, the concept of a particle, something with mass, with boundaries, with a definite position, was nonsensical. So what filled this space? Some cosmologists speak of a quark-gluon plasma, a state of matter so energetic that quarks and gluons, the building blocks of protons and neutrons, roamed freely, unbound by the strong force. But even this plasma is too structured for the earliest moments. Before the quark-gluon phase, there may have been something stranger, a state where particles were not yet particles, but excitations in fields that had not yet learned how to vibrate in stable patterns. These proto-particles flickered into existence and vanished, unable to hold their form in the chaos. They were ghosts of matter, rehearsing the shapes they would one day take. Yet some believe the story goes deeper still. Perhaps the first objects were not excitations at all, but topological knots, twists and braids in the fabric of space-time itself, frozen for a fraction of an instant before unraveling. These knots would not be made of anything. They would be geometric features, defects in the structure of reality, like the wrinkles in a folded sheet. When the sheet smooths, the wrinkles vanish. But for a moment, they are real. They have location. They have energy. They could, in principle, interact. And this is where the story bends. If particles are knots in space-time, then matter is not a substance. It is a shape. It is geometry pretending to be solid. This idea is not new. Ancient philosophers intuited it. Form precedes substance. Plato spoke of perfect shapes underlying the material world. Aristotle argued that potentiality becomes actuality through structure. Modern physics has returned to these insights, clothing them in mathematics. String theory, for example, proposes that particles are not points but loops, one-dimensional strings vibrating in higher dimensions. The different vibrations produce different particles, an electron here, a quark there. But before the strings could vibrate stably, there may have been a phase where the strings themselves were unstable, fragmenting and reconnecting in a kind of preharmonic noise. Others propose preons, hypothetical particles smaller than quarks, smaller than electrons, fundamental constituents from which all other particles are composed. If preons exist, they would be the alphabet of matter, the letters that combine to spell protons, neutrons, photons. But here a question emerges. If preons are particles, what are they made of? The regress threatens to continue infinitely, each layer revealing another, smaller layer beneath. Unless, of course, the question itself is wrong. Unless particles are not made of anything. Unless they are endpoints, irreducible features of reality that emerge from pure mathematics, from symmetry, from information. And this is where the emotional weight of the inquiry becomes almost unbearable. We are accustomed to thinking of matter as stuff, tangible, solid, real. We trust our senses. We touch a table and feel resistance. We see a star and assume its light originates from something substantial. But the deeper we probe, the more substance dissolves. Particles are excitations. Fields are abstractions. Space-time is foam. And beneath the foam, there may be nothing at all, or rather, nothing that resembles the physical world we inhabit. There may be only structure, only pattern, only the skeletal logic of how things relate. Seconds after the Big Bang. At this scale, the universe was smaller than an atom, denser than a neutron star, hotter than any temperature we can name. Classical space-time breaks down. Quantum mechanics and general relativity, our two most successful theories, give contradictory answers. We cannot say what happened. We can only speculate. Some suggest that time itself was quantized, ticking forward in discrete jumps rather than flowing smoothly. Others propose that time was emergent, a property that crystallized from a timeless substrate. In such a universe, the question, what came first, loses meaning. There was no first. There was no sequence. There was only a superposition of all possible configurations, collapsing into one. Yet the truth may be stranger. Loop quantum gravity, an alternative to string theory, suggests that space-time is woven from tiny loops, quantum threads stitching reality together. At the Planck scale, these loops form a network, a fabric so fine that it appears continuous from a distance, but discrete up close. In this model, the first particles were not objects moving through space. They were ripples in the fabric itself, disturbances propagating through the network. And before the ripples could form, the network had to exist. But what gave rise to the network? Here we confront the edge of knowledge, the boundary where physics becomes philosophy and philosophy becomes poetry. Some models propose a pre-Big Bang phase, a contracting universe that collapsed to a point and then rebounded, creating the expansion we observe today. In this scenario, the first particle of our universe might have been the last particle of a previous one, compressed to unimaginable density and then released. The cycle repeats eternally: contraction, bounce, expansion, contraction. Each universe inheriting the quantum residue of its predecessor. Each particle carrying a memory of previous existences. The emotional resonance of this idea is profound. It suggests that creation is not singular but recursive, that the universe is not born from nothing but from itself, endlessly renewing. Others turn to the concept of vacuum energy, the idea that empty space is not truly empty but seethes with virtual particles and fields at their lowest energy state. Before particles could exist stably, the vacuum itself may have been in a higher energy state, a false vacuum, unstable and eager to decay. When it decayed, it released energy, and that energy condensed into the first real particles. But this raises another paradox. If the vacuum itself is a field, and fields are collections of potential particles, then what is the vacuum made of? The question spirals inward, each answer revealing a deeper layer of uncertainty. And here we arrive at a possibility both unsettling and elegant. Perhaps the first particle was not a particle at all, but a unit of information. In recent decades, physicists have increasingly viewed reality through the lens of information theory. Quantum states can be described as bits of information. Black holes store information on their surfaces. The universe itself might be a vast computational process, evolving according to rules we are only beginning to decode. In this framework, particles are not fundamental. Information is. A particle is simply a way that information organizes itself, a pattern that emerges when certain bits correlate in specific ways. If this is true, then the question, what was the first particle, transforms into what was the first bit of information. And here the answer may be disarmingly simple, a binary distinction. A yes or no, a 1 or 0. The moment the universe differentiated, When something became distinguishable from nothing, when here separated from there, when now diverged from then, that was the first bit. Everything else followed from that initial split. Particles, fields, space-time, galaxies, consciousness, all elaborations of that primordial binary choice. Yet even this picture, elegant as it is, invites further questions. What enabled the distinction? What forced the universe to choose 1 over 0, to break its perfect symmetry? Some invoke quantum fluctuations, random jitters in the void that tipped the balance. Others appeal to anthropic reasoning. The universe chose because only such a choice could lead to observers capable of asking why. Still others suspect that the question itself is anthropomorphic, that we impose the language of choice and causality onto a process that simply is, without reason, without motive, without prior state. The emotional weight here is not just intellectual. It is existential. We seek origins because we seek meaning. We want to know that the universe came from somewhere, that it had a reason for beginning, that our existence is not an accident but a consequence of deep principles. Yet the further we trace the chain of causation, the more it dissolves. The first particle, if it existed, was not a beginning but a transition, a moment when one kind of uncertainty gave way to another. And before that moment, there was not nothing. There was something we do not yet have words for. This is the subplancian abyss, a place or non-place, where geometry itself is unstable, where space-time has not yet congealed, where the distinction between matter and energy, particle and wave, existence and non-existence, blurs beyond recognition. To enter this realm is to abandon certainty, to accept that the universe, at its core, is not made of things but of relationships, not of substance but of structure, not of answers but of ever-deepening questions. And perhaps that is the truest answer we will ever find, that reality is not a collection of objects but a pattern of patterns, infinitely complex, infinitely beautiful, infinitely elusive. And yet, as we stand at the edge of this conceptual void, a new question emerges, quiet but insistent. Perhaps the first particle was not matter. Perhaps it was not even energy. Perhaps it was information, a distinction, a correlation, a bit of difference that propagated forward, branching and evolving, until it became the universe we inhabit. And if that is true, then the story of the cosmos is not a story of things. It is a story of knowing, of structure, of meaning emerging from the interplay of abstract relations. And that story, as we shall see, leads us to an even stranger possibility, that consciousness itself may be woven into the fabric of reality from the very beginning. What if the first particle was not a thing at all, but a thought? Not a thought in the human sense, not consciousness, not intention, but something more fundamental, a distinction, a binary choice, a single bit of information that split the void into two states, yes and no, here and there, something and nothing. This idea, radical as it sounds, has gained traction in recent decades as physicists probe the deepest layers of reality and find not substance, but structure. Not matter, but mathematics. Not particles, but patterns. And patterns, at their core, are information. They are arrangements, correlations, relationships encoded in a medium we have yet to fully understand. Perhaps the universe is not made of particles that carry information. Perhaps the universe is information, and particles are merely the way that information expresses itself in spacetime. This reframing is not idle speculation. It emerges from multiple lines of inquiry that converge on a single, unsettling conclusion. Information may be the primary substance of existence. Consider quantum mechanics, where a particle does not have definite properties until it is measured. Before measurement, It exists in a superposition, a state of multiple possibilities. The act of observation collapses the superposition, forcing the particle to choose one outcome. But what is being collapsed? Not a physical object, but a wave function, a mathematical description of probabilities. And probabilities are information. They are statements about what could happen, encoded in the structure of the universe itself. When the wave function collapses, information becomes actuality. A bit flips from uncertain to certain. A decision is made. But here a question emerges. Who or what decides? In the earliest moments of the universe, there were no observers, no conscious beings to collapse wave functions, no instruments to measure outcomes. Yet the universe differentiated anyway. Symmetry broke. The inflaton field decayed. Virtual particles became real particles. Energy condensed into matter. Something happened, and that something required information to be processed, distinctions to be drawn, states to be selected from a space of possibilities. The universe, in effect, observed itself. It measured its own state and collapsed into existence. And if that is true, then the first particle was not a physical object that appeared in space. It was the first bit of information that made space possible. This idea finds its clearest expression in the work of physicist John Archibald Wheeler, who proposed a doctrine he called it from bit. The phrase is deceptively simple, almost playful, but its implications are profound. Wheeler suggested that every physical quantity, every particle, every field, every force, derives its existence from binary choices, from yes or no questions answered by the universe at the quantum level. Reality, in this view, is not a collection of objects, but a collection of answers. A particle exists because the universe has said yes to a particular configuration of information. Space extends because the universe has encoded distance as a relationship between bits. Time flows because information propagates, one decision leading to the next in an unbroken chain. Yet the truth may be stranger. If information is fundamental, then matter is optional. A particle is not a small, hard pellet of substance, but a localized pattern of information, a knot of correlations, a nexus where bits converge. And this raises a disquieting possibility. Perhaps particles are not real in the way we assume. Perhaps they are emergent, like the pixels on a screen that collectively produce an image, but individually mean nothing. Zoom out, and you see a face. Zoom in, and you see only dots. Which is real, the face or the dots? The question has no clear answer, and that ambiguity infects our understanding of reality itself. We perceive particles because our senses operate at a scale where information clusters into recognizable patterns. But at deeper scales, the patterns dissolve, revealing only the raw data from which they are constructed. This is where the holographic principle enters, an idea so strange that it seems ripped from science fiction, yet grounded in rigorous mathematics. The principle states that all the information contained within a volume of space can be encoded on the surface that bounds it, like a hologram that stores three-dimensional information on a two-dimensional film. Applied to the universe, this suggests that everything we experience, all matter, all energy, all events, is a projection from a lower dimensional surface, perhaps the edge of space-time itself. We live inside the hologram, mistaking the projection for reality. And if this is true, then the first particle was not an object that emerged in three-dimensional space. It was a ripple on the surface, a disturbance in the boundary, a bit of information written onto the cosmic hologram that only later appeared to us as a particle moving through volume. The emotional resonance of this idea is profound and unsettling. It suggests that the universe we inhabit is not fundamental but derived, not primary but secondary, not the real thing but a shadow cast by processes occurring elsewhere, at scales we cannot access. And yet, the hologram is not an illusion. It is a valid description of reality, perhaps the only description we can ever know. We are not outside the hologram, looking in. We are part of it, woven into its structure, emergent patterns within a larger pattern. Our thoughts, our memories, our sense of self, all of it encoded on the surface, projected inward, experienced as depth. And the first particle, in this scheme, was the first projection, the moment when the surface began to encode volume, when flat information began to simulate dimension. But there is a deeper problem. If the universe is information, what is the medium that stores it? Information does not exist in a vacuum. It requires a substrate, a hard drive, a piece of paper, a brain, something to hold the bits. In classical computers, bits are represented by electrical charges or magnetic orientations. In quantum computers, by the states of atoms or photons. But what stores the information of the universe? Some physicists propose that space-time itself is the medium, that the geometry of space encodes data in its curvature, its topology, its quantum fluctuations. Others suggest that the medium is even more abstract, a network of relations, a web of correlations with no physical embodiment, a pure logical structure that exists independently of matter or energy. This leads to a radical possibility. Perhaps the universe is a computation, not a simulation running on some alien supercomputer, but a self-executing algorithm, a program that reads and rewrites itself at every instant. The laws of physics are not external rules imposed from outside, but emergent properties of the computation itself, patterns that stabilize as the program evolves. Particles are subroutines. Fields are data structures. Space-time is the memory architecture. And consciousness, the subjective experience of being, is what it feels like to be a subset of the program observing another subset. Information reflecting on information, the universe becoming aware of itself through localized processes we call minds. And here the emotional weight shifts from wonder to something more unsettling, a kind of cosmic loneliness. If reality is computation, if particles are data, if matter is emergent and space is projection, then what is real? What can we hold on to? We touch a table and feel solidity, but the solidity is a pattern of information, a correlation between the bits encoding the table and the bits encoding our hand. We see a star and feel its light, but the light is a wave of information propagating through space-time, collapsing into photons only when it interacts with our retina, triggering neural signals that our brain interprets as brightness, distance, beauty. The star is not out there in some absolute sense. It is a shared hallucination, a consensus reality constructed by information processing systems. Us, embedded in a larger information processing system, the cosmos. Yet some believe the story goes deeper still. If information is fundamental, then the first particle was not just a bit, but a meaningful bit, a piece of data that correlated with something, that pointed beyond itself, that created a reference. Information without context is noise. A random string of ones and zeros means nothing. But the moment one bit correlates with another, meaning emerges. The first bit says here. The second bit says not here. Together, they define space. A third bit says now. A fourth says then. Together, they define time. The universe, in this view, did not begin with substance. It began with syntax, with the grammar of relationships, with the rules that allow bits to combine into structures, structures to combine into objects, objects to combine into galaxies, galaxies to combine into the observable cosmos. This idea has deep roots in ancient philosophy. The pre-Socratic thinker Heraclitus spoke of the logos, the rational principle underlying all change. He did not mean a God or a consciousness, but a pattern, a logic, a structure that governed the flow of events. Modern information theory echoes this insight. The universe is not a collection of things, but an unfolding algorithm, a process governed by rules that are themselves encoded in the structure of the process. There is no need for an external lawgiver. The laws are intrinsic, woven into the fabric of information itself. And the first particle was the first instance of the law, the moment when the abstract rule became a concrete example, when potential became actual, when information became experience. But here a paradox emerges, quiet but insistent. If information is primary and particles are secondary, then where does information come from? In classical physics, information is conserved. A system can change, but the total amount of information remains constant. Yet the universe, by all accounts, began in a state of minimal information, a singularity, a point of perfect symmetry with no distinguishing features. How did it transition from minimal information to the vast complexity we observe today? The second law of thermodynamics tells us that entropy, a measure of disorder, or equivalently, of missing information, increases over time. The universe is becoming more disordered, more spread out, more homogeneous. Yet locally, complexity arises. Stars form. Planets coalesce. Life emerges. Intelligence evolves. How can complexity increase while entropy increases? The answer lies in a subtle distinction. Entropy measures the information we don't have about a system. Complexity measures the information the system contains. As the universe expands and cools, it creates niches where information can organize itself into structures, where local decreases in entropy are paid for by global increases, where meaning can crystallize out of noise. And this is where the emotional tone shifts again, from loneliness to something closer to awe. If the universe is a computation that generates complexity, that organizes information into ever more intricate patterns, then we are not accidental byproducts. We are part of the process. We are the universe's way of processing information, of reflecting on itself, of asking questions about its own origin. Our minds are subsystems within the cosmic computation, localized regions where information achieves self-reference, where the program becomes aware of the code. And the first particle, in this expanded view, was not just a bit of data. It was the first step in a process that would eventually lead to us, to consciousness, to curiosity, to the capacity to wonder about the first particle. But there is still a deeper question, one that resists all attempts at resolution. If the universe is information and information requires processing, then who, or what, processed the first bit? In a classical computer, the processor is external to the program. It reads instructions, executes operations, updates memory. But the universe has no external processor. It processes itself. It is both the program and the machine, both the data and the algorithm. This self-referential structure is deeply puzzling. It suggests that the universe is not a passive object, but an active subject, not a thing that exists, but a process that occurs, not a noun, but a verb. And the first particle was the first moment of that verb, the instant when the universe began to act upon itself, to differentiate, to compute. Some models propose that the universe is a quantum computer processing information at the Planck scale, where spacetime itself is quantized. Each tiny region of space is a qubit, capable of holding a superposition of states. The evolution of spacetime is a quantum computation, proceeding according to the laws of quantum mechanics, which are themselves information processing rules. In this picture, the first particle was the output of the first quantum computation, a measurement result, a collapsed wave function, a bit of information that transitioned from superposition to definite state. But what triggered the collapse? In standard quantum mechanics, collapse requires an external observer. But at the beginning, there was no external. There was only the universe, observing itself, collapsing its own wave function, bootstrapping reality into existence through a kind of self-measurement. And here we confront the edge of comprehension, the boundary where physics blurs into metaphysics, where science becomes indistinguishable from poetry. If the universe observed itself into existence, then consciousness, or something like it, may be woven into the fabric of reality from the very beginning. Not human consciousness, not awareness in the sense we experience it, but a kind of proto-awareness, a capacity for self-reference, a structure that allows information to fold back on itself, creating loops, creating mirrors, creating the conditions for experience. Perhaps the first particle was not just a bit of information, but the first moment of interiority, the first instant when the universe was not just a collection of states, but a system capable of knowing its own state. This idea is speculative, untestable, perhaps untestable in principle. But it resonates with a deep intuition that many have felt, that the universe is not dead, not mechanical, not a clockwork automaton grinding through predetermined motions. It is alive with possibility, saturated with potential, perpetually creating itself anew. And we, as conscious beings, are not separate from this process. We are expressions of it. Our questions about the first particle are the universe's questions about itself. Our wonder is its wonder. Our search for meaning is its search for meaning. And perhaps that is the truest answer we will ever find. That the universe is not a thing we observe from outside, but a process we participate in from within, a computation that includes us as subroutines, patterns within patterns, information reflecting on information. Yet even this picture, beautiful as it is, leaves unanswered the most fundamental question of all. If the universe is information, if particles are bits, if reality is a self-reading program, then what is the origin of the program itself? Where did the first bit come from? Who wrote the code? Or, more unsettling still, is there no code? Only an infinite regress of information generating information, patterns generating patterns, with no ground, no foundation, no ultimate source? Some say the question is meaningless, that causation breaks down at the origin, that the universe simply is, without reason or purpose or prior state. Others invoke quantum mechanics, suggesting that the first bit arose from a fluctuation, a spontaneous symmetry breaking, a random event in a space of all possible events. Still others turn to mathematics, proposing that the universe is not a computation running on hardware, but a mathematical structure existing in an abstract Platonic realm, independent of time, space, or physical instantiation. And here the emotional weight becomes almost unbearable. To trace the chain of causation back to its origin is to find not a beginning, but a question mark. The first particle, if it existed, was not an answer but a deepening of the mystery. It did not explain existence. It exemplified it. It was the moment when the universe transitioned from one kind of unknowing to another, from the chaos of infinite possibility to the structure of definite actuality. And that transition, that collapse, that first bit, it was not an event that happened in the universe. It was the event that was the universe, the instant when information became reality, when abstraction became experience, when the code began to run. And now, as we stand at the edge of this conceptual abyss, a new question emerges, quiet but relentless. If the first particle was a bit of information, if matter is emergent and space is projection, if the universe is a self-executing computation, then who, or what, processed the first information? What read the first bit? What collapsed the first wave function? What observed the first observation? The question leads us to the threshold of the unknowable, to the possibility that consciousness itself may not be a late arrival in the history of the cosmos, but a primordial feature woven into the structure of reality from the first instant. And that possibility, as we shall see, opens a door to the strangest territory of all, the suggestion that the universe is not just information, but awareness, that it does not just compute, but experiences, that it is not just a program, but a mind. We have traveled backward through time, past galaxies and stars, past atoms and quarks, past fields and foam, past geometry and information, searching for the first particle. And now, standing at the edge of all models, all theories, all explanations, we confront a truth more unsettling than any answer we might have found. Every explanation we have constructed requires something to already exist. The first particle cannot be first if it emerged from a field, because then the field was first. The field cannot be first if it arose from quantum fluctuations, because then the laws governing fluctuations were first. The laws cannot be first if they are mathematical structures, because then mathematics was first. And mathematics cannot be first if it exists in some Platonic realm, because then the realm was first. Each answer we propose opens a door to a prior question, and that question opens another door, and another, in an infinite regress that offers no ground, no foundation, no place to rest. This is the final paradox, not a puzzle to be solved, but a condition to be accepted. The search for the first particle has led us not to a beginning, but to the realization that beginnings may be illusions, artifacts of the way our minds organize experience. We think in terms of before and after, cause and effect, origin and consequence. But the universe may not. It may simply be, without needing to have begun, without requiring a first moment or a first thing. And yet, this answer, if it can be called an answer, feels unsatisfying, incomplete, a retreat from the quest rather than its fulfillment. We want to know why there is something rather than nothing. We want to trace the chain of causation to its source. We want the universe to make sense on our terms. But perhaps it does not owe us that courtesy. Consider again the inflaton field, the primordial energy that preceded particles. Where did it come from? Some say it emerged from quantum fluctuations in a pre-existing vacuum. But a vacuum is not nothing. It is a state of minimal energy, a configuration of fields at their ground state, seething with virtual particles that flash in and out of existence. The vacuum is structured. It obeys laws. It has properties. So the inflaton did not come from nothing. It came from something, a something that itself demands explanation. And when we try to explain the vacuum, we invoke quantum field theory, a mathematical framework that describes how fields behave. But where did quantum field theory come from? Not as a human invention, but as a feature of reality. Why does the universe obey these particular equations and not others? Why are there fields at all? Some respond by appealing to deeper principles, symmetries, conservation laws, invariances that constrain what can happen. These principles are elegant, powerful, predictive, but they are not explanations. They are descriptions. They tell us how the universe behaves, not why it behaves that way, not why it exists in the first place. And here a question emerges. Are the laws of physics discovered or invented? Do they exist independently of the universe, governing it from some abstract realm, or are they emergent properties of the universe itself, patterns that stabilize as the cosmos evolves? If the laws are independent, then they are prior to the first particle, and we must explain their existence. If they are emergent, then they cannot account for the first particle, because the particle had to exist before the laws could emerge from its behavior. The same paradox afflicts every model we have examined. The holographic principle suggests that reality is a projection from a lower dimensional surface. But what is the surface? Where did it come from? What are its properties? And why those properties rather than others? The information universe proposes that particles are patterns of bits, correlations in a cosmic computation. But what is computing? What reads the bits? What executes the algorithm? Wheeler's "it from bit" tells us that physical quantities derive from yes or no questions answered by the universe. But who asks the questions? What forces the universe to answer? And what existed before the first question was posed? Loop quantum gravity envisions space-time as a network of quantum threads, a fabric woven from discrete loops. But what are the loops made of? Not matter, not energy. Those are emergent. The loops are supposed to be fundamental, irreducible features of reality. Yet they have properties. They can connect, disconnect, form nodes, propagate disturbances. These properties imply structure, and structure implies prior conditions, prior rules, prior reasons. The regress continues. String theory posits that particles are vibrations of one-dimensional strings in higher dimensions. But what are the strings? What makes them vibrate? What determines the number and nature of the dimensions? Each answer generates new questions, and the questions multiply faster than the answers can contain them. And here the emotional weight becomes profound, almost oppressive. We have spent centuries building knowledge, layer upon layer, each generation standing on the shoulders of the previous, confident that we were approaching ultimate understanding. We discovered atoms, then nuclei, then quarks. We unified electricity and magnetism, then added the weak force, then glimpsed the outlines of a theory that might unify all forces. We thought we were closing in on the final answer, the ultimate explanation, the theory of everything. But the closer we look, the more the ground dissolves beneath us. Every answer reveals deeper questions. Every explanation requires unexplained assumptions. Every model rests on foundations that cannot themselves be modeled. Perhaps this is not a failure of science, but a revelation about reality itself. Perhaps the universe is not the kind of thing that can have a complete explanation. Perhaps it is fundamentally self-referential, a strange loop where the whole contains the parts and the parts contain the whole, where cause and effect form cycles rather than chains, where every element depends on every other element in a web of mutual dependence that admits no starting point. In such a universe, the question, what was the first particle, is not just unanswered but unanswerable, not because we lack knowledge, but because the question presumes a structure, linear causation, temporal priority, distinct origination, that reality does not possess. This idea is not new. Ancient philosophers grappled with it under different names. The Buddhist concept of dependent origination suggests that all phenomena arise in dependence on other phenomena, with no independent, self-existing entities. Everything is conditioned. Nothing is absolute. The chain of causation has no beginning and no end, only an eternal flow of interdependent arising and passing. Hindu cosmology speaks of cycles within cycles, universes born and destroyed in endless succession, with no ultimate origin, no first cause, only the eternal dance of Brahman, the unchanging reality underlying all change. Greek philosophers debated the problem of infinite regress. If everything has a cause, then causes have causes, and those causes have causes ad infinitum. Aristotle proposed an unmoved mover, a first cause that itself is uncaused. But this solution only relocates the mystery. Why is there an unmoved mover? Why does it have the properties it has? Why does it move anything at all? Modern physics has rediscovered these ancient puzzles in new language. Quantum mechanics tells us that particles do not have definite states until measured, but measurement itself is a physical process involving particles. General relativity tells us that space-time is curved by matter, but matter is defined by its motion through space-time. Information theory tells us that information requires a substrate, but the substrate is made of particles, and particles are patterns of information. Everywhere we look, we find circularity, self-reference, mutual dependence. The universe is not a linear story with a clear beginning, middle, and end. It is a network of relationships, each element defining and being defined by the others, with no privileged starting point, no foundational layer, no bedrock of pure, unquestioned existence. And yet, the paradox deepens. Even if we accept that the universe is self-referential, that it needs no external cause, that it simply is, we are still left with a mystery. Why does it exist at all? Why is there something rather than nothing? Nothing would be simpler. Nothing would require no explanation. Nothing would have no properties to account for, no laws to derive, no structure to justify. But there is not nothing. There is something. There is this vast, intricate, beautiful, terrifying cosmos, filled with stars and planets, atoms and organisms, thoughts and dreams. And that something, its sheer existence, remains unexplained and perhaps unexplainable. Some physicists have tried to define nothing, to give it mathematical rigor. They say the universe could have arisen from a quantum vacuum, a state of minimal energy. But as we have seen, a vacuum is not nothing. It is a highly structured, law-governed state. Others propose that the universe began as a quantum fluctuation, a random blip in the fabric of possibility. But fluctuations obey probability distributions, and probability distributions are mathematical structures. Where did the structure come from? Why does mathematics describe reality at all? Why is the universe mathematical rather than something else, chaotic, arbitrary, lawless? The question, why is there something rather than nothing, transforms into why is there order rather than disorder, and then into why is there mathematics rather than non-mathematics. Each reformulation of the question reveals another layer of assumption, another implicit precondition that we cannot account for. Perhaps the mistake lies in the question itself. Perhaps why is a human construct, a category we impose on a universe that does not operate according to reasons or purposes. In our lives, we act for reasons. We want food, so we eat. We seek knowledge, so we study. We desire connection, so we reach out to others. Cause and effect are linked by intention, by motive, by the pursuit of goals. But the universe does not want anything. It does not seek anything. It does not have intentions. It simply unfolds according to rules. Or perhaps it is the unfolding, the rules emerging from the process itself, with no external reason, no cosmic purpose, no ultimate why. And if that is true, then the question, what was the first particle, is a category error, an attempt to apply human concepts of causation and temporality to a process that transcends them. But there is a deeper problem still. Even if we abandon the search for a first cause, even if we accept that the universe is eternal or self-causing or beyond causation altogether, we are still confronted with the mystery of this universe. Why these laws and not others? Why 3 spatial dimensions and 1 temporal dimension? Why the particular values of the fundamental constants, the speed of light, the strength of gravity, the mass of the electron? If even one of these constants were slightly different, atoms could not form. Stars could not ignite. Life could not emerge. The universe appears fine-tuned for complexity, for structure, for the emergence of observers capable of asking why it is fine-tuned. Is this a cosmic coincidence? A statistical necessity in a multiverse where every possible universe exists? An artifact of anthropic reasoning. We observe a life-permitting universe because we could not exist in any other? Or is there something deeper, something we have not yet imagined, that explains why the universe has the particular character it does? And here we arrive at the heart of the paradox, the place where all roads converge and all explanations fail. The search for the first particle has revealed not an answer, but a limit, a boundary to what can be known, a horizon beyond which even the most sophisticated theories cannot penetrate. Every model we construct, every explanation we propose, rests on assumptions that themselves require explanation. And those explanations rest on deeper assumptions, and those on deeper still, in an endless descent that offers no final resting place. We have discovered not the origin of the universe, but the limits of origin itself, the possibility that beginnings are not features of reality, but features of our minds, tools we use to organize experience, narratives we tell to make sense of a cosmos that may be, in its deepest nature, beyond sense-making. This realization is both humbling and liberating. Humbling because it reveals how little we truly understand, how fragile our knowledge is, how vast the unknown remains. Liberating because it releases us from the demand for absolute certainty, from the need for final answers, from the illusion that the universe must conform to our expectations. Perhaps the deepest wisdom is not knowing, but wonder. Not certainty, but curiosity. Not answers, but questions that open onto further questions, inviting us ever deeper into the mystery. And the first particle, in this expanded view, is not a fact to be discovered but a symbol, a marker of the boundary between what can be explained and what must simply be experienced, between the knowable and the ineffable, between science and awe. Yet even now, standing at the edge of the unknowable, we cannot help but ask one more question. If every explanation requires a precondition, if every origin demands a prior origin, if the universe resists all attempts at complete description, then perhaps the problem is not with the universe, but with our concept of beginnings. Perhaps time itself does not extend infinitely into the past. Perhaps the Big Bang was not an event that happened in time, but the event that created time, the moment when temporal sequence began. And if time had a beginning, then the question, what came before, is meaningless, not unanswerable, but nonsensical, like asking what is north of the North Pole. There is no before, because before is a temporal concept, and time did not exist before time began. But this answer, elegant as it is, only deepens the mystery. If time began, what caused it to begin? What triggered the transition from timelessness to temporality? And what does it even mean for something to exist outside of time? Without time, there is no change, no causation, no sequence of events. There is only a static, eternal present, a condition so alien to our experience that we can barely conceive it, much less explain how it gave rise to the dynamic, evolving universe we inhabit. And so the paradox returns, closing the circle, leaving us where we began, with wonder, with mystery, with the recognition that the first particle, if it existed, marks not the end of ignorance, but the beginning of a deeper, more profound unknowing. And perhaps that is enough. Perhaps that is all we were ever meant to find. Perhaps we have been asking the wrong question all along. Perhaps the universe did not begin with a particle, or a field, or a fluctuation, or an informational bit. Perhaps it did not begin at all. We have searched for a first moment, a point of origin, a seed from which everything grew. But what if there is no seed? What if the universe is not a story with a beginning, middle, and end, but a pattern that simply is, eternal, self-sustaining, requiring no birth because it never was not. This possibility unsettles us because it contradicts the deepest structure of our experience. We are born. We age. We die. Everything we touch has an origin and a terminus. The sun rises and sets. Seasons cycle. Civilizations rise and fall. We live in a world of beginnings and endings, and we have projected that structure onto the cosmos itself. But the cosmos may not share our temporal architecture. Consider the possibility that time itself is not fundamental. Physicists have long suspected this. In quantum gravity, in certain formulations of string theory, in Wheeler-DeWitt equation of quantum cosmology, time does not appear as a primary variable. It is emergent, a derived quantity, a way that change manifests when viewed from inside the system. But if time is emergent, then it had no existence before the universe, or rather, there is no before the universe, because before is a temporal concept that only makes sense after time has emerged. The Big Bang was not an event that happened at a moment in time. It was the moment when moments became possible, when sequence crystallized out of timelessness, when the universe transitioned from a state of eternal being to a state of temporal becoming. And if that is true, then the first particle was not the first thing to exist. It was the first thing to exist in time, the first member of the temporal sequence, but not the origin of existence itself. This reframing is profound. It suggests that the universe did not come into being, but has always been, not in the sense of existing for an infinite duration, because duration presumes time, but in the sense of being beyond time, prior to time, encompassing time as one of its features rather than being contained by it. Imagine a tapestry woven from countless threads. From within the tapestry, you might trace a single thread and ask where it begins. You follow it backward, through loops and crossings, and eventually you reach what seems like a starting point. But zoom out, and you see that the thread is part of a larger pattern, that the pattern has no edge, no border, no place where it starts or stops. It simply is, complete and whole, with every thread necessary to every other thread, none of them first, none of them last, all of them co-arising in mutual dependence. But here a question emerges. If the universe is eternal, if it has always existed in some form, then how do we account for the Big Bang? The evidence is overwhelming. Cosmic microwave background radiation, the expansion of space, the abundance of light elements, the large-scale structure of galaxies, all point to a moment approximately 13.8 billion years ago when the universe was unimaginably hot, dense, and small. How can we reconcile this apparent beginning with the idea of eternal existence? Some cosmologists propose that the Big Bang was not a beginning, but a transition. Before the Big Bang, there may have been another phase, a contracting universe that reached a minimum volume and then rebounded, a quantum state that decayed into classical spacetime, a multiverse process that continually spawns new universes, each with its own Big Bang, its own timeline, its own illusion of being first. In these models, our universe is one bubble in an infinite foam, one note in an eternal symphony, one iteration in a cycle that has no start and no end. The first particle of our universe was preceded by the last particle of a previous universe, or by a field configuration in a larger cosmos, or by a quantum fluctuation in a metastable vacuum that has existed forever. The chain of causation does not terminate. It loops back on itself, or extends infinitely in both directions, or forms a network with no privileged center, no ultimate source, no foundational ground. And if this is true, then the search for the first particle is like asking for the first number. There is no first number. For every number you name, there is a smaller one. The sequence extends infinitely, and the question of where it begins is revealed as a category error, an attempt to impose finitude on the infinite. Yet the truth may be stranger still. Some physicists and philosophers have proposed that the universe is not just eternal in time, but eternal in possibility, that it encompasses all possible states, all possible configurations, all possible histories simultaneously. In the many-worlds interpretation of quantum mechanics, every quantum event spawns a branching of universes, each branch realizing a different outcome. You measure a particle's spin, and the universe splits. In one branch the spin is up, in another it is down. Both branches are equally real, equally existent. There is no single timeline, no definitive history, only an ever-expanding tree of actualized possibilities. And if this is true, then the first particle was not a unique event that happened once. It happened in infinitely many ways, in infinitely many branches, each slightly different, each giving rise to a different cosmos, a different arrangement of matter and energy, a different story. This view dissolves the concept of first entirely. There is no first particle because there is no single sequence of events. There are only patterns, correlations, structures that emerge when we trace particular paths through the tree of possibilities. From our perspective, embedded in one branch, it appears that there was a beginning, a moment when our universe came into being. But from a larger perspective, if such a perspective is even meaningful, there is only the eternal unfolding of all possible universes, each one containing observers who believe themselves to be first, who search for origins, who construct narratives of creation. And all of them are correct, and all of them are mistaken, because they are asking a question that presumes a structure the multiverse does not have. And here the emotional weight shifts, from the vertigo of infinite regress to something softer, more accepting, almost peaceful. Perhaps the search for the first particle was never about finding an answer. Perhaps it was about the journey, the process of inquiry, the way that asking deepens us, humbles us, connects us to the cosmos we are trying to understand. We are not separate from the universe, observing it from outside. We are part of it, expressions of it, localized patterns in the same fabric we are studying. Our questions are the universe's questions. Our wonder is its wonder. And perhaps the ultimate insight is not knowledge, but recognition, the realization that we are not seeking something external to us, but something we already are, something we have always been, something that cannot be found because it was never lost. Consider the beauty of a galaxy, spiraling slowly through the void, its arms sweeping through space like a cosmic brushstroke. Does the galaxy need a beginning to be beautiful? Does it matter whether it formed 5 billion years ago or has existed eternally? The beauty is in the pattern, in the grace of the motion, in the interplay of light and gravity and time. And perhaps the universe is the same. Its beauty does not depend on having an origin. It does not require a first moment to justify its existence. It simply is, and that is enough. The stars do not ask why they shine. The planets do not question why they orbit. They participate in the dance, and the dance is its own meaning, its own purpose, its own justification. But there is still a pull, a human need, a desire to understand not just what is, but why it is. We are meaning-making creatures. We cannot help but ask. And so we construct models, theories, narratives, stories that give shape to the chaos, that impose order on the flux, that allow us to feel we have grasped something true about reality. And perhaps these stories are not discoveries, but creations, not reflections of an objective truth, but constructions that help us navigate experience. The first particle, in this view, is not a fact waiting to be uncovered. but a concept we invented to organize our understanding, a placeholder in a narrative structure that makes sense to us even if it does not correspond to anything in the universe itself. This does not mean the search was futile. It means the search was human. We ask questions because we are curious. We build theories because we seek patterns. We tell stories because we need coherence. And in doing so, we participate in the universe's self-exploration, its ongoing process of understanding itself through the consciousness that arises within it. We are the universe waking up, looking back, asking where it came from. And the answer we find, or fail to find, is less important than the fact that we asked. The question itself is the miracle. The wonder itself is the revelation. And yet, as we stand here at the end of our journey, having traveled backward through time and forward through possibility, having explored particles and fields, geometry and information, paradox and mystery, we are left with a quiet, persistent intuition. Perhaps the first particle was not created because creation itself may be an illusion. Perhaps nothing ever comes into being or passes away. Perhaps existence is not a process but a state, not an event but a condition, not a story but a structure that contains all stories, all moments, all possibilities in an eternal, unchanging whole. Time flows for us because we are embedded in it, moving along a trajectory from past to future. But from outside time, if such a view is meaningful, there is no flow. There is only the complete four-dimensional space-time, a frozen sculpture containing every event that ever was or will be, with no moment more real than any other, no particle more first than any other. In this block universe, as it is sometimes called, the Big Bang is not an event that happened long ago. It is a region of space-time, a boundary condition, a place where certain parameters take certain values. And the first particle is not a thing that came into existence at a moment. It is a feature of the structure, a thread in the tapestry, a note in the eternal chord. It exists timelessly, as do all particles, all moments, all events. The appearance of creation, of becoming, of temporal flow, is a perspective effect, a consequence of our position within the structure, our limited view of a totality that we can never fully grasp. And if this is true, then the question, what was the first particle, is like asking, what is the first point on a circle? There is no first point. The circle simply is, complete and whole, with every point necessary to the integrity of the shape. And here we arrive, finally, at a kind of cosmic peace. Not the peace of knowing, but the peace of acceptance. Not the satisfaction of an answer, but the serenity of surrender. The universe does not owe us explanations. It does not conform to our categories. It is larger, stranger, more mysterious than any framework we can construct. And that is not a failure. It is an invitation to remain curious, to stay humble, to keep asking even when answers elude us, to find beauty not in certainty, but in the endless unfolding of discovery. The first particle, if it existed, marks the beginning of our story, not the beginning of existence. It is the point where we start counting, the moment we single out as significant, the threshold that separates the comprehensible from the incomprehensible. But the universe was here before we began counting. It will be here after we stop. It does not depend on our understanding to exist. And perhaps that is the deepest lesson of all, that reality is not diminished by our ignorance, that mystery is not a gap to be filled but a feature to be celebrated, that the cosmos is most beautiful not when explained, but when contemplated in wonder. We are finite beings in an infinite universe, brief sparks of consciousness in an eternal expanse, asking questions that may have no answers. And yet we ask, and yet we search, and yet we wonder. And in that wondering, we touch something larger than ourselves, something that connects us to the very fabric of existence, something that makes us, in our small way, participants in the grandest story ever told. The story of a universe that may never have begun, but that continually becomes, through us and through all conscious beings aware of itself. And so we return to where we started, but transformed by the journey. We asked what was the first particle, and we have found that the question opens onto deeper questions, each one revealing more of the mystery, none of them providing the final answer we sought. We have learned that origins are elusive, that beginnings may be illusions, that the universe is not a simple chain of cause and effect, but a complex web of relationships, each element connected to every other in ways that defy linear narrative. We have glimpsed the possibility that time itself is not fundamental, that existence may be eternal, that the cosmos is not a thing that was created but a pattern that simply is, beyond birth, beyond death, beyond the categories we use to organize experience. And in that glimpse, we have found something unexpected, not despair at the limits of knowledge, but liberation. Liberation from the need for certainty. Liberation from the demand for complete understanding. Liberation to wonder, to question, to explore without expectation of final resolution. The first particle, whether it existed or not, whether it was matter or energy, field or information, substance or structure, has led us to this place, a place of profound not knowing, of cosmic humility, of openness to mystery. And perhaps that was the destination all along. Not an answer, but a deeper appreciation of the question. Not knowledge, but wisdom. Not certainty, but awe. The universe unfolds around us, vast and ancient, beautiful and terrible, filled with stars and galaxies, atoms and organisms, thoughts and dreams. It does not need a beginning to be miraculous. It does not require a first particle to be whole. It simply is, and we are part of it, expressions of its infinite creativity, witnesses to its unending transformation. And that is enough. That has always been enough. The first particle may never have been first. It may simply have been the first thing we noticed, the first thing we could name, the first thing that made sense in a cosmos that transcends sense-making. And in noticing it, in naming it, in wondering about it, we have participated in the universe's self-reflection, its ongoing exploration of what it means to exist. And that participation, that wonder, that endless questioning, that is the true gift, the real discovery, the deepest answer we will ever find.